How are you?
Yeah, good, good.
How do you do it?
Pardon me?
No, nothing. Yeah.
Yeah, it's going okay.
Tarak, when did you move to IIT Delhi?
It's been 6 months, last June. Yeah,
Okay.
just after the pandemic, the second.
you?
Yeah, good, good.
How do you do it?
Pardon me?
No,
How are things on your
It's
side?
going okay.
It's going well. Tarak, when did you move to transitioning?
It's been 6 months, last June. Oh.
Yeah, I think we can start in a minute, Tarak.
Yeah, sure.
We will be joining.
Sure.
Yeah, I think we are ready to go.
Okay, so. Okay, shall I start?
Yes. Yeah,
Okay,
please.
good. So, very good morning to the people in India, and I think good evening to the people on the other side of the globe. And I guess it's very early morning for my European friends. So, first of all, let me thank one more time the organizers, Nishant, Pratyush, Jagannath, Andrew, and Professor Chandra for organizing such a wonderful conference. And each of the talks is loaded with exciting stuff, new ideas, and I'm sure all participants are kind of enjoying it. And some of them are getting new ideas, believe me. And then, so as I was telling Nissan that for me, I attended 2014 RARE meeting, and when I was a graduate student, and the stuff that I learned, that was my first exposure to enhanced sampling and the community. And the stuff that I learned from there really helped me during my PhD and kind of gave me a new direction to my career. Anyway, so I'm really grateful, and it's great to be back here again in RARE21. And I was looking at some pictures shared by Pratyush on Twitter, and it's been great. So anyway, let's start the morning session of day 3 of RARE21, and we have 5 speakers, 2 before the break, tea break, and 3 after the tea break. So the first speaker is Professor Deva Priyakumar, who is an associate professor, or I guess full professor, at IIT Hyderabad, and his research group is interested in doing research on applying machine learning techniques to understand or explore chemical reactions. And lately, he's been doing a lot of stuff on deep learning. And today he's going to talk about enhanced sampling and exploration of chemical reactions. So with this, let me invite Professor Deva Priyakumar to share his screen and start the presentation. Over to you, Professor Deva. Thank you.
Can you hear me? Hello?
Yes, we can hear you clearly.
You can see my screen also, right?
Yes.
Yeah, thank you very much, Tarak, for a nice introduction, and also thank you. I thank all the organizers, Nishant, Pratyush, Jagannath, and Andy, and everyone for Professor Chandra and everyone for kindly having me in this conference. So today I'm going to talk about slightly on a different topic than most of the lectures here. This is about exploring the chemical space, right? So I will get to get to that slowly. But just to quickly introduce, my group at IIT, for the past 12 years, we have been looking at basically chemical and biological systems and processes using traditional computational methods. And recently, we started looking at how we could use the data-driven methods for like analyzing molecular dynamics trajectories, or looking at how we can use for different tasks in molecular sciences, right? So that's basically what I'm going to talk about today, right? So before I dive into the chemical space exploration, I thought I will quickly take a couple minutes and then tell how we ended up in this particular space, right? So we have been working on this particular problem for a long time, where we look at protein and RNA folding equilibrium and how this equilibrium is affected with respect to different perturbations, like chemical perturbations, thermal perturbations, mechanical perturbations, and so on. And then try and understand, what are the factors that influence the free energy surface, right? So the picture that I show here is just the free energy profiles from umbrella sampling simulations of a very simple system, trip cage protein. Yesterday also there was a talk where the trip cage was shown. I'm sure in this kind of conferences, trip cage is a frequent proposition. So we do like the free energy calculations, like umbrella sampling, or the thermodynamic integration, or even quantum mechanical calculations to try and understand, right? So why, what are the reasons, or what are the driving forces behind the factors that affect these free energy profiles of the protein folding, right? So that led to many other studies in terms of using what we get from this understanding, and then understand many other biological processes, right? So one of the this is again an example where we look at the free energy of folding of, or unfolding of RNA, I should say, where with respect to different temperatures and with respect to different conditions, you look at how the RNA goes from folded to unfolded state, right? See, one of the issues, Jagannath gave an excellent talk on how you choose collective variables, and there are several other talks, right? So one of the the things that we were having issues, or we were thinking about, was that why should, as a chemist, I decide what the collective variable is, right? So if I know the dynamics of the system, is it possible to learn this collective variable in an unsupervised manner, right? So I will skip this one. This is kind of too elementary for this audience. But this is something that we developed 4 or so years ago, where we said, like, I have a macromolecular trajectory, and then I want to learn some kinetic properties of this particular system. And then we developed a method using unsupervised machine learning and graph theory, just for analyzing these trajectories. Like, basically take the trajectory and then represent these snapshots using some feature vector, and then do a dimension reduction, either using principal component analysis or any other dimensional reduction technique, and then use the unsupervised method, where you do a density-based clustering, which is basically a TSNE method, and then use expectation maximization. These also, yesterday Nilanjana spoke about expectation maximization in her talk, right? So basically the idea is, like, without having to introduce any bias in terms of defining what the reaction coordinates are, we let this method figure out itself, starting from a very complex system with thousands of degrees of freedom, and then come up with a simple understanding of the probable pathways. The advantage of this method that we showed, for example, here, what is the ground truth is 1 in the blue, and what we get from this method is what is given in orange or red, right? So in this case, we didn't even have the time information. We just took the long trajectory, just remove the time information, and then shuffle these trajectories, and then we provide this to the method, and then it's able to still come up with these qualitative kinetic properties. So this was published 4 or so years ago. And for some reason, I don't know, I mean, it did not get much traction. So basically the idea is that this was the first study where we started from where we were in terms of doing molecular dynamic simulations, free energy calculations, and then trying to, use machine learning for doing simulations, or to analyze these trajectories. To think of it, maybe we should have used machine learning on the title, I don't know. All right. So anyway, so today, most of my talk is going to be around enhanced sampling and efficient exploration of chemical space. I will introduce the topic, but for the sake of students in the audience, quickly go through. In traditional computations, what do? We basically start from an input. Let's call it X, and then we calculate properties of this particular system, right? So in some sense, we know X, that's the input. We know F, for example, quantum mechanics or statistical mechanics and so on. So the prescription is given by the by physics, and then we use this to calculate the properties, right? So what is how is it different from machine learning? Machine learning basically is saying that I'm not going to use any physics, right? At least at the bottommost level, saying I just take examples of systems where X and Y are known, right? I take several examples of system where X and Y are known, and then now I try to figure out what the F is, or in other words, instead of we telling the computer this is the prescription, use this prescription to calculate a property, right? We ask the computer saying, if this is my input and this is the corresponding output, what do you think, or what is the prescription based on which I get the I map X to Y, right? Basically we map X to Y and then get the function out. So once we have the function, I can do a similar or the traditional way of doing computations using the new function. Okay. So of course, I'm not going to go into the details. Typically this is a neural network. Yesterday Jagannath gave a nice introduction to how neural network works, what the weight is, what the bias, what is the activation function, and things like that. So. And then the second, nowadays people, we keep talking about deep learning, right? So basically the idea is like, in the traditional machine learning, we have an input from the chemist or a biologist where, who kind of engineers these features, or you take the original input and then using the chemical or biological wisdom, we try to come up with features that are important for learning a given property. And then we give those features as input to the neural network, and hence the function is y equals f of x prime, right, instead of x. So in deep learning, what we do is we basically use a deeper neural network where the network learns the features by itself, right? And this is physically not so very, or physically not quite understandable, right? Doesn't make much sense. And then now it's defined as y equal to f of z. Right, just to give one example, recently what we said was, let's say I simulate a liquid organ system, right? So if I use a DFT or like ab initio dynamics, right? If I'm using DFT functional, right? We get reasonably good numbers out, and we are very close to experiment in some of the in some of the properties, right? And of course, if you take classical. If you take the force field potential, we typically use Lennard-Jones potential, and it does pretty well, right? But then of course there is a difference. Okay, so what we said was that the Lennard-Jones potential is good enough to calculate the forces in this particular system of liquid organ. Now, is it possible to bridge this gap, saying we calculate the forces using Lennard-Jones potential and then supplement it with the delta function, right, which will which can then be added to this force, and then do a simulation on top of that, just like how we would do in a classical MD simulation. So that's basically what we did for this. What we do is, like, with respect to the positions of the atoms, we calculate the delta F in this case, and then we use that to calculate different properties. In this case, for example, if you look at the diffusion constant, this is the experimental numbers. This is coming out of delta net FF, and this is the from the Lennard-Jones potential. So the advantage here is that, of course, we do the simulations faster than DFT. Not only that, but we also can increase the system size. Now we can go to larger systems just by learning based on a smaller system, and then do calculations at a larger length scale and time scale, which works out really nice. So I will skip this and then move to the main part of my talk, where when you come to these machine learning and deep learning methods, they are data hungry, in the sense that they need a lot of data to learn from, and then from that you try to learn, right? But then there are ways, how do we circumvent this problem, right? So when I say exploring or enhanced sampling of chemical space, we're talking about this. So let us say small organic molecules, right? So when I say known chemical space, these are molecules that have been synthesized at least once, Okay, so it's about 800 million is the current number, right? And this is the space that we have already seen at least once or so, right? So now let us say my task is to go through this particular known chemical space and then choose some interesting molecules based on whatever properties or whatever characteristics that I'm looking at, right? So obviously, even if you take the cheapest, the most inexpensive method, if you take, going through this, a billion molecules is not going to be easy. And hence, most of the times, we restrict ourselves to a certain region of sampling. It could be random, it could be based on certain features and so on. But then, our sampling region is very, very small, right? If I do that, if let's say the green and red dots are the interesting ones for me that I would have eventually ended up identifying if I was able to screen all of them, right? So I would have identified both the green and the red, but because I'm restricting my sampling to a certain region, I'm going to only identify these things, missing out on this rest of the points that I'm actually interested in. And then the other major point is that if you consider the overall chemical space, right, it is estimated to be about 10 power 60. And then of course you have a large number of molecules that obviously we cannot have access to because, we haven't seen this space in some sense. So the question is, starting from here, right, the space that is, practical to actually sample, and how do we learn about all of the known chemical space? That's the first question, that we enhance the sampling, right? And then the second one is, is it possible to again do the same thing based on learning from here and explore the sampling in the general chemical space, right? So for the first problem, the enhanced sampling problem, where we go from the smaller sampling space to all of the known chemical space, we use something called the Gaussian process. Right. So I'm going to take a simple example first, and then go back to molecules. I'm going to digress for a couple slides here. Right. So let us take a simple system. Right. So it's a helium plus H2 plus system. It reacts to give this particular product. Right. So this is a potential. Basically the potential surface of this was fitted to an analytical function, right, which is addition of a 3-body term and two body terms, which is given by this. But how do we get this? Basically we calculate energy points on a large number of energy points using very high level of theory like the CI and so on, and then you get these points and then do a fitting and then get the expression for the potential energy surface. Now the question is it possible to represent this potential energy surface by sampling as less points as possible? Right. So that's the idea. So, let us say, right, I'll start from the farmost, the graph here. I hope you can see my pointer. So let us say this is my, actual potential energy surface, which is given in solid blue line. All right. So now what is it I want? I want to map this particular surface by sampling as less points as possible. Right. So, the Gaussian process works like this, where you start from a bunch of functions, which kind of believes that, the function is, somewhere in this particular, or the final surface is somewhere around here, right? So you start from there and then choose a random number of points. Let's say choose 1, 2, 3, 4, 5 points, right? So now you try to fit the functions, or, you train the Gaussian process by fitting these 4 points now, right? So now you can see that, at these 4 points, you are doing very well, right? So now, at every point, you can evaluate the, value of the function, right? In terms of the mean and the variance, basically the prediction of the y with respect to any x, and then the uncertainty with respect to that. That's basically the gray line here, right? So that, this movie would possibly explain it better. So this is the, the prior that I start with, and I'm going to start sampling. This is the first point. That's the first sample that I'm taking. Now I start doing the Gaussian training process. So now I, start choosing different points on the surface, and then, move towards reducing the uncertainty in this particular case. But the objective need not be reducing the uncertainty in all the problems. It again depends on the, the problem at hand, right? So as you can see, now, we have moved closer to the actual, surface, just by sampling these, the green, the orange points here, right? So if we do that, the question is now, let us say I have sampled a number of points, and then I would like to sample more points and then go. But my objective is to sample as less number of points as possible, right? So we use something called an acquisition function, which lets me choose the points, which helps me choose optimal points, which will help me move towards my objective, right? So in this case, it could be the upper confidence bound, where this is the prediction of the energy at the mean, and then this is the sigma of the Gaussian, and then there you have a scaling factor k, and then by adjusting this factor lets us exploit. That means if I'm interested in one particular area of the of the surface, I can use this term to move there, and then if my objective is to explore all of the surface, I can use appropriate value for the kappa, and then I can move, right? Just to give results for this before moving back to the molecular problem, right? So this is the ground truth of the H2 plus potential surface, right? So this is the ground truth, right? Fitted based on tens of 1,000 points typically, all right? So this is what you get from the Gaussian process just from sampling 300 points. It's not so bad, right? Of course there are places for improvement, but it does pretty well. So going back to the molecular problem, now what is that I want to do? I want to use Gaussian process by exploring a certain surface and then identify molecules of interest. Or in other sense, what I'm interested in is perform only a fraction of the total number of molecules, calculations on the molecules, but still recover all of the top hits. So if you remember, I showed two, the red and green dots, right? So I would like to still sample as less points as possible, but I'm greedy to kind of identify all the top hits, right? So we propose this method called memes. That's just that's the meaning for memes. But see, the idea, maybe I'll go to the next slide and try to explain. So we start from small molecule database, right? We tried multiple different sizes of databases, all starting from 250,000 all the way to 100 million compounds. And then basically we use molecular featureization. Again, this is something that Jagannath explained it nicely yesterday, use of autoencoders, and then how you use the latent space to represent your molecule, right? So and then you do a simple k-means clustering and then choose a set of initial points, right? And then you can do whatever evaluation you want. In this case, we just perform docking of this particular molecule with respect to a given protein, right? So now, what is the objective? I want to identify all top hits which show a higher binding affinity towards a given protein, right? I'm going to use the Gaussian process where you have the same as what I mentioned before, except that this is a little bit more complex, right? So that's the the surrogate function that we use for the Bayesian optimization is the deep Gaussian process. And then for selecting the next important points, right? I spoke about upper confidence bound. So in this case, we use expected improvement as the acquisition function. And now we do iteration in terms of we choose a new point, train a Gaussian process, evaluate all the molecules, and then wherever the uncertainty is high, you move towards that region and then keep iterating this particular process, right? So this kind of captures that. What you have at the bottom is the acquisition function, and this is the actual Gaussian process that is being trained, right? So let us say the black one is the actual surface, and then these points are the ones which have been sampled. The true label is known, right? So the advantage of this particular method over the traditional ML or DL methods is that you don't have to necessarily have labels, or labels meaning outputs, for every single point that you're evaluating for the training, right? You can do the labeling on the fly if that is possible, right? So that's the acquisition function and the Gaussian process that's training. And in the expected improvement, we look at the maximum and then sample a point there. So if you see, there will be some point sampled, and then with respect to every maximum, we keep extra sampling, and then try to get to this particular region. So in this case, my objective is not to get or represent the function exactly. I'm not even worried about representing the function exactly in the lower binding affinity regions. So, I'm only interested in the high binding affinity regions, and then I can use this to move towards that and identify all possible molecules. Just to quickly give results, right? So let us say, I have this, like 100 million compounds, right? So if I cannot do calculations on 100 million compounds, and then I just, choose randomly, let's say 6% of these molecules, right? So that would mean that the number of top hits that I identify will be approximately 6, right? Assuming that it is uniformly, the interesting molecules are uniformly distributed in the database. So what that would mean, traditionally, if I do this computation, this will slowly, approximately linearly go and then meet 1 at 100, right? So that's how we traditionally do. But then if we employ means, just by sampling 6% of the total, all the molecules in the data set, we are able to kind of get almost all of the top hits, close to 96 or 97%. Okay, so I don't think I'll have time to speak about the deep means, but it's just the different Gaussian process, because Gaussian process it does not computationally scale beyond let's say hundreds of thousands. So hence we had to move to the deep Gaussian process. So this Venn diagram kind of captures this. So if I have to, let us say, I do 3 exercises or 3 experiments where we apply memes and then get 500 top hits. If I take all of the data set, all 100 million, I take the 500 top hits, and then I randomly choose and I take the 500 top hits, right? So just by sampling 6%, right, we are able to identify, almost 490 top compounds, right? So now, how can, can this be like, I showed, it could also be applied to, constructing potential surfaces. Now can we use this for doing the actual enhanced sampling technique? I do not know. Jagannath and I were supposed to talk about it sometime, but I've been lazy. Okay, so now we can extend it to multiple dimensions, in the sense that whenever we are trying to look or design a molecule, we are not looking at one property, right? So we want to satisfy a number of properties before we choose a molecule, right? So that means you would like to do this selection with respect to number of properties, right? So let us say the blue one is the distribution of couple properties. Let's not worry about what they are. And that's how the distribution looks like. So now, of course, let's say I cannot do, explicitly calculate all of them, right? So now I'm saying I'm interested in molecules in this particular region. So if I use these multi-objective memes, right, you can see that the molecules that are being picked are, more and more in this region than in the bottom, right, and so on. Okay, so now I think I have close to 4 minutes. I will close it soon. So the second aspect is the exploration, right? So, from the practical space, how do you move towards exploring new space? So in other words, one of the questions that people have been asking is that, in a typical machine learning problem, we try and map X to Y using a function, right? On the other hand, is it possible to do the inverse, saying, can we, based on the known examples, can we map Y to X, right? If you are able to do that, the only question that we have to ask this algorithm to do is like, I am interested in a molecule with a certain property. Can you generate that molecule? And then the actual output of this algorithm would be the molecule instead of the other way around, right? So I'm gonna skip this and then talk about the first part only, right? So basically, idea is like, is it possible to identify molecule with desired properties? There's a lot of work going in this particular area, but primarily applying these methods like the recurrent neural network, general adversarial network, variational autoencoder, and reinforcement learning. So I will just take one example and then close, right? So, quickly, what is reinforcement learning? This is, a game that most of us know in India. I think it's called Piñata in Spain. I don't know. So anyway, so the idea is that, a person is blindfolded, right? And then is randomly positioned somewhere. And then the objective is this person has to go and break the pot, which is hanging, at some point, right? So let us say there is a teammate who is directing this person towards the pod, right? So if the person starts walking away from the pod, right, obviously, the teammate is not going to be amused, going to possibly start, shouting or something. And then if the guy is actually moving towards the pod, the teammate is going to say, oh yeah, move right, move left, and so on, right? So reinforcement learning works very, very similarly, where I have a network, right? Typically RNN mostly these days, and we have started exploring graph-based methods recently in general, not just us, but in general the community, where this is a network which basically generates molecules, right? In this case, this guy can just keep moving, right? So this can generate a molecule. It understands the chemistry language, and then it generates valid molecules. So now, and then it performs an action, right? What is the action? This starts to move, and then this person says, yes, no, or no, and so on, right? So similarly, we have an environment which evaluates the properties of these molecules and then says whether it's the right move or not, right? So it gives a higher reward if the property is close to what we are thinking, and then it could penalize the model when it is moving away from where we want, right? So I think the next next slide will clearly say. So let us say I am asking this particular model to generate molecules whose log P values are between 0 and 5. It's between the two lines, right? So if I do, without any conditioning, if I do a generation and look at the distribution, it is going to look like this. So now this is not what I want. These are not regions that I'm interested in. Now I have a reward function. In this case, it could simply be a Gaussian here. So that could be the reward function where more and more you are within this range, you get a more reward, right? So, and similarly in this case, this is just a simple measure for how easy or difficult it is to synthesize a molecule. So lower it's better, higher it's harder. So basically I'm trying to minimize this. So in this case I can have a reward function which is an exponentially decreasing function, where more and more you move towards the left, you get a higher reward, right? So in this case, okay, I'll skip. I'll just show how this thing works. So now you can see that with respect to different iterations of learning, you see that the distribution moves towards the middle in this case, and the distribution moves towards the left in this particular case. So I think with this I should stop. Just in summary, just machine learning tools seem to be a powerful addition to the computational chemist toolkit for molecular design, and in general sciences also, in addition to the technology domains. And in this in the last 3 or 4 years, we have been able to show that the modern machine learning methods can make this molecular design or molecular understanding pipeline much more efficient. So with that, I should thank the coworkers from whom I have learned a lot, and then funding from different sources over the years, and then the collaborators, and finally thank you for your attention. I hope I didn't take too much time. Thanks.
Thank you, Professor Deva, and we are perfectly on time. So before reading out the questions from the chat box, let me quickly ask you one question. So the features that you use for the chemical reactions and the ligand binding, what kind of are they? They are molecular graphs or?
Which one? Sorry, which one you said?
Chemical reactions and the ligand binding in 2 cases. The features.
For this one, you said, right?
Yeah.
For this one, I hope you can say. I'm not able to find.
Yeah, the molecular descriptors.
Right, so basically, you have autoencoder, right? So in this case, we use the smiles notation. It's a simple, one-dimensional string, right? Mm-hmm. So the last function would be the difference between the output and the input. We minimize that, and then have a bottleneck here. That's the latent space, which on which each of the molecules are represented. I hope I answered that.
Okay. Yeah, that's the one. Great. So thank you. Let me read out the question from Jagannath. Can you elaborate how in your JCTC paper, I think the first paper that Delta Net FF, you came up with time information from replication in molecular dynamics? So I guess it's a data
That
generation.
is not the Delta Net effect. That was the one which was Chatterjee et al. At the very beginning when you talked about
Okay, 2018 JCTC. Yeah.
You mean this one?
No, at the very beginning you had this slide, correct? Where you talked, yeah, correct. So in this part, the next one you had this, you had the title of temporal correlations that you were trying to find from REMD data using machine learning.
Oh, okay. All right. So, basically, I think you are asking about this. Basically, when I said that we removed the time information, so we took a really long trajectory, right? So I can't remember how long it was at this point, but we took a long trajectory where the system actually goes from folded to an unfolded state, right? Multiple of them, and then showed that this method, we compared the pathway that we get from Markov state model and from this, right? When the Markov state model uses time, right? For if you have a one bit of one long trajectory, you have time information, and you can get this. So now, with this particular method, what we do is we remove the time information and then shuffle the trajectories and then do the same. And then that's exactly what I show here. So that I show here. So the red one is from the Markov state model, which uses the time information. So the blue one is the one which we have removed the time information and use this particular method to, get this part. I hope I answered.
All right.
Yeah.
Okay, thanks. So Brian, would you like to ask your question or you want me to read out? So he wrote, do you have insight as to whether the surrogate models are actually interpolating or extrapolating in chemical space, or simply picking up on similarity in a narrow neighborhood around each molecule?
Oh, yeah, that's a very good question. So actually, when we do generations, right? So we do look at the quality of the generations by several metrics. One of them is to look at how similar and how different they are, right? So sometimes we would like to generate similar molecules. Sometimes the objective is to generate different molecules. I'll show this particular example. So in this case, for example, we want to generate molecules with this constraint, saying, I want all the molecules that we generate to have this particular scaffold, right? So if you look at the generated molecules, you see all of them have that particular scaffold. I didn't talk about it today. We use transformer decoder model to do this. But in general, when the objective is to sample the all of the chemical space, we ensure that the diversity is maximized. Yeah.
So this non-Gaussian process in chemical space, he's asking, do you think heteroscedastic Gaussian process could be of use?
What Gaussian process? The last part, can you please repeat?
He said that non-Gaussian nature of chemical space distributions and docking scores, do you think heteroscedastic Gaussian process could be of use?
Yeah, I will have to read about this. I do not know. I don't think I even got what that was. Something Gaussian process. So I do not know. Sorry.
Yeah, so you can look at it later on.
Yeah, I will look at the chat. Thanks.
Yeah, Anand has a question. He said, in terms of reinforcement learning, sensing is local, I assume, and in that case, for certain landscape, there are chances of being reinforced into local minimum. How do we circumvent that without the knowledge of final state? So in the reinforcement learning.
Yeah. Yeah, that's a tricky problem. So that's one of the yeah, I don't think it's straightforward to answer, but the idea is that you generate multiple models for this and then look at how different or similar they are, or the distribution of the molecules with respect to distribution of different properties like similarities and things like that, and then check. So and hence RL is actually not the method of choice when it comes to molecular generation, though there's quite a amount of work is available. So slowly people are I think the variational autoencoder is better. Yeah.
Okay. I see. Thanks. So with this, thank you very much, Deva.
Thank you. Thanks. Thanks, everyone. Yeah, thank you.
Let's move on to the next speaker. Our next speaker is Professor Sapna Sarapriya, and who is an associate professor in the Department of Chemistry, University of Minnesota, United States. And her group is currently interested in molecular dynamic simulation of condensed matter systems, nucleations, and surface science. And she'll be talking about navigating path towards nucleation in complex systems. So over to you, Sapna.
Thank you, Tarak. Can you all hear me okay and see the slides?
Yes, very clearly. Please.
All right, so hello everyone, and thanks for hanging around to listen to the talk. I will also begin with thanking all the organizers for, navigating COVID and organizing this workshop online and trying to navigate all the time zones as well. So thanks for doing that. This is my first RARE meeting, and I hope it's not my last. With all of the stories I've been listening about the in-person meetings, I definitely want to try and be part of that. Please note, organizers. All right. I also wanted to start by thanking all the students who did a really, really good job with the poster session, and I wanted to congratulate all of them. I really enjoyed looking at as many posters as I could. I also wanted to note that some of you may have noticed that the chats kind of disappeared if you logged out and logged in. According to Remo, they're having a technical issue with the storage system, and that's why the chat history is not there. So I wanted to mention it because I lost my chat history with many of you students. So please know that I just didn't disappear. All right, with all of that, I'll get started. So I'm going to tell you, a few stories about the work that we have been doing in studying nucleation in complex systems. And really, when I say complex systems, our systems of choice are related to water. So we think of water in its pure form as well as aqueous solutions. So the two main systems that we have been thinking about from a nucleation perspective for many years now is ice nucleation and gas hydrate nucleation. And in doing this, we have done method development, both on the front of structural analysis. So this were, we recently developed a machine learning based method to characterize structures. And then that approach actually allows us to differentiate between 16 different ice structures, which really enables us to analyze our data much better than using traditional order parameters. And this work is being presented by Stephen Hall, my students, in the posters. And then we've also, of course, developed new sampling techniques. This is just something that you end up doing if you're trying to study problems like nucleation. And our main choice of method when we had started this work was forward flux sampling. And what we did was able to extend it out into multiple dimensions. So we developed what we call contour forward flux sampling, which essentially allows a multidimensional sampling system. But over the years, we have, in addition to forward flux sampling and contour forward flux sampling, also collected a lot more repertoire of methods that we use to tackle these problems. So we've also used transition interface sampling. And in fact, we've spent considerable time thinking about what are the effective and practical ways of making sure that you're doing your forward flux sampling or your transition interface sampling correctly, and how you can monitor them well. So we recently just submitted a manuscript, which is a practical guide on how to do FFS and TIS. So for those who are interested in thinking about these methods, keep an eye out for it. And then we've also thought about synergizing experiments and simulations. And in a way, this is like doing a multi-scale simulation. And then one of the other things that we focused on is how do we make our simulations computationally efficient. So all of these advanced sampling methods are great, but they're expensive. And if you want to think about generating data, we just heard in the last talk, right? Machine learning is data hungry. So if you want to generate that level of data, you have to figure out ways of doing these simulations very effectively. So we've been thinking about that, and we developed a method that we call rigid seeding. So today I'm going to share these two stories with you. So I'll start with telling you how we were able to bridge experiments and simulations to study ice nucleation, and then how that's all of our past studies, how it's leading us to rigid seeding method. So I'll give you a very quick introduction of why we are even interested in this problem of ice nucleation. So more specifically, what we're interested in is in heterogeneous ice nucleation. So here we are thinking about how surfaces affect this phase transition of liquid water to solid ice, right? So here I'm showing you some data from atmospheric chemistry, and they're very interested in looking at what are the particles, these dust particles in the environment, and how is this affecting the phase transitions of water. So you're looking at the composition of what dust might look like in the atmosphere. So you have many different types of dust, and then this is telling you what their ice activity is. And you can see that different molecules, different types of molecules have different types of ice activity. Now, if you zoom into one of these, which is of our interest, which is a mineral dust, you see that even in mineral dust, you have a broad variety of different types of minerals. And if you look at their respective ice nucleation behavior, it's quite different, right? So some minerals like K feldspar is a very good ice nucleator. Quartz is somewhere in between, and then mica is a poor nucleator. So a very natural question for anyone to ask is, why do these surfaces have different ice nucleating behavior? And a natural intuition-based, approach would be to say, oh, it must be related to their hydrophobicity or philicity, and we heard Amish talk about this as well. And or it's related to their ability to hydrogen bond or lattice match, etc. Right? So of course, people, when they started thinking about this, those are the kind of guiding principles they use. And turns out that none of them actually are good in describing why these different surfaces behave differently. So that's where we came into the picture, and we said, okay, simulations can in principle really do this, and they can tell us the answer to these questions. So we started with sort of two main questions. One is we wanted to know, how do various surface properties affect ice nucleation? And if we understood this, then we should be able to develop methods such that we can rapidly screen through ice nucleating agents, right? So this should then help us design new materials that could either be inhibitors or promoters for ice. And this is sort of the vision that we've been working towards. So over the years, we've studied a large number of different surfaces. We started with looking at silver iodide, which is one of the best ice nucleators out there. And we looked at surface charge distribution effect. We looked at kaolinite, which is another mineral surface. We looked at the effect of changing the lattice matching and the hydrogen bond flexibility. And so this was a collection of 10 or so surfaces. And essentially, if you put all of the results together, it showed us that the surfaces that promoted ice nucleation also promoted very specific orientations of water molecules in the metastable liquid water. So this was kind of exciting to us because it said that if we can characterize the water structure of the metastable liquid water, we might be able to predict the ice nucleating behavior and not have to do very long simulations to sample ice nucleation in the simulations. So then we said, okay, this is great. Let's extend it out to more interesting surfaces. Now, while we were thinking about that, we also wanted to bridge experiments and simulations, because every time I presented the AGI and kaolinite surface, you would always have some experimentalists say, yeah, but these surfaces are too perfect for experiments, right? So how do you bridge and how do you study the same system in experiments and simulations? So, and I approached Will Cantrell, who is a professor in physics at Michigan Tech, and I'd met him at one of these ICE conferences. And we had a very good conversation. So I contacted him and I said, look, I can study ice nucleation in simulations. I want to bridge experiments and simulations. How do we do that? Let's think about it. So we thought about it a lot, and we were thinking about what are the different surfaces we can study. So some of the criteria that we had was, one, the surfaces had to be the same in experiments and simulations, right? And two, we should be able to change the same parameter in experiments and simulations to see how the system is responding so that we can then bridge the observations from experiments and simulations. So after a lot of thinking, we decided, well, we can study muscovite mica. And here is why. So mica looks something like this, right? So it has these layers of silica and Al and oxygen, which are then bound together through these ions. And what you can literally do is you can, peel out this layer. You can literally take a macroscopic sample and peel it with, a little bit long nails. And what will happen is you'll expose this surface with, some ions on one side and some ions on the other. So this is the top view of the same peeled surface that you're seeing. And these orange spheres, you see other ions. Typically, there's potassium ion in the naturally occurring mica. Now, as you peel, the advantage is that these surfaces that you expose are atomistically smooth in experiments, which means that now simulations and experiments can be on the same footing. And the second thing is that when you take this surface and expose it to solutions of different salts, you can exchange out the cation. So you can change this potassium, which is in the natural state, to other cations, and you'll see that in the next slide. This means that we can change the same parameter both in experiments and simulations and see how the system responds. So that's what we did. So we did droplet freezing experiments. I say we, Will and his student did that. And they exchanged out potassium with all of these different ions. So you can see we have 3 divalent ions and 1 trivalent ion. In our simulations, because we have non-reliable, I should say, force fields for these trivalent of magnesium and strontium, we decided to stick with just potassium and calcium ions. And we basically performed simulations that look something like this. We have the surface, the specific cation, liquid water, and then we just did long simulations of the supercooled liquid in this interfacial region. All right. So from the experiments, this is the results that we got, right? So here what I'm showing you is the nucleation rate on these surfaces, and this is per centimeter square per minute. So it's normalized by time and by the area as a function of temperature. And you can see that as you increase the valency, so as you go from potassium to the divalent to the trivalent cations, the nucleation rate is increasing. That should not have happened. Okay, sorry. The nucleation rate is increasing, right? So this tells us that as we increase the valency of the ions, the nucleation rate on the mica surfaces increases. So of course, the next question is to think about why that happens. And these are the different reasons that could probably be contributing. So maybe it's the contact area, which essentially means that as you're changing the ions and you put a droplet of water, the contact area of that droplet of liquid water changes, and that can then affect the nucleation rate. But because we normalize the nucleation rate by the contact area, that cannot be a factor explaining this difference in the nucleation rates. The second piece could be that you have surface roughness, and nucleation is very sensitive to surface roughness. So what could be happening is that you exchange out the ions, it causes some form of surface roughness, and then that helps ice nucleate. So we, with a collaborator, performed very detailed AFM studies to characterize the surface roughness, and it found that the surface roughness between these different surfaces is not very different, and therefore that does not explain why we see a difference in the nucleation rate. So now the only thing remaining is that the cations are causing this difference, and that has to be related to the structure of water. So then it indicates to us that these cations are changing the structure of water that's in contact with the surface, and that change is leading to the change in the nucleation behavior. Now, to tease out how the structure of water is changing, you cannot rely on experiments. These are very hard experiments to do, and this is where the simulations then come into picture. So we ran the simulations. We obviously did many different types of characterizations to see if we can tease out what is happening. And I'm only going to show you the ones that showed us some correlation, right? So I'm going to essentially in the next few slides show you 2 or 3 main things. One is I'm going to show you the clusters of hydrogen bonded water molecules, and specifically I'll show you the size of these clusters. And then I'm going to talk about 3 types of water essentially. So what we do is we take the interfacial region, and then we look at the water molecules in that interfacial region as whether they're in the first hydration shell of the ion, the second hydration shell of the ion. And if they're neither in the first or the second hydration shell, we call them free waters. So what you'll see me showing in the slides is talking about the first hydration shell water, second hydration shell, and free water. You'll see this for the interfacial region, but we'll also show you the fraction of free water in these clusters of hydrogen bonded water molecules. Right, so we did this, and this is the result that my students showed for the potassium and calcium ions, right? So here, what you're looking at is the probability that you observe a cluster greater than a given size. And you see that you have a very high probability of observing clusters that are, let's say, greater than 40 or 45 in case of potassium rather than calcium. And this was really surprising because what I was expecting to see is the opposite result. Because then I could say, yeah, the cations are resulting in higher hydrogen bonded clusters, and therefore they're better nucleators. But this was completely opposite. So I did, what naturally you do when a student shows this is say, something is wrong in your calculation, go check it again, right? So of course my student did, it was right, this is what we were getting. So, the power of simulations is also visualization. So we looked at these clusters very carefully, and we colored the water molecules in the cluster based on whether they were in the first hydration shell, the second hydration shell, or free water. And by just looking at this, you can see that even though this is a big cluster on potassium, the amount of this cyan, which is the free water, is lesser than, let's say, in calcium, right? So this told us, maybe it's also the fraction of free water that's important, because then the free water can reorient to form structures that look more ice-like. So we then quantified this. We looked at the fraction of free water in the interfacial region and the fraction of free water in these hydrogen bonded clusters. And you see that the fraction of free waters is higher for calcium in both cases than for potassium. So this tells us that it's the contribution of free water that's probably helping with the enhanced ice nucleating behavior. So of course, we wanted to also see if this extends out to higher valency ions. And because, as I said, for these trivalent ions, force fields, especially for these mineral systems, is not really available, we decided instead to just take our original ions and increase and decrease their charge. So we took K plus and just added a charge to it to make K2 plus and K3 plus, and then we took calcium, reduced by 1 to make it Ca plus, and then increase to do it Ca3. And then we did essentially the same analysis, and we found, I don't know if I have that slide. Yeah, and we found that indeed the cluster sizes were larger, but also the fraction of free water was much larger when you had these trivalent ions. And so this logic that it's also the fraction of free water that's contributing to the improved nucleation seemed to hold across these different valencies, right? So the picture that emerged from this analysis for the nucleation on mica surfaces was the following. So we think that large water clusters are forming via hydrogen bonding, and the water molecules in the ionic hydration shells anchor these clusters. And then as the charge increases, there's a higher fraction of free water, and that higher fraction allows the water to reorient and adopt ice-like structures, and hence ultimately becomes a better ice nucleating agent, right? So then one very natural question to ask is, why do fewer ions lead to larger sizes of hydrogen bonded clusters? And then why are there more ice-like particles in mica surfaces with ions of higher valency? And you can imagine that when you have higher valency, you have lesser number of ions, which means you're exposing more of the mica surface without ions, which we are going to call here bare mica. So then the natural question is to say, is the bare mica surface helping? So to look into that, what we did was we created these types of surfaces, where what we've done is we've taken the ions that were initially randomly distributed on the entire surface, and we shifted them to one side of the surface so that we expose a large bare mica patch. And we did this both for potassium and for calcium, and we did it for K3 plus and Ca3 plus just because we have less number of ions in those cases. And then we did the same analysis, etc., but I'm only going to show you like one snapshot, which essentially conveys the idea. What we first observed is all of the hydrogen bonded clusters were pretty much populated on the bare mica surface. So that tells us that the bare mica helps, the formation of these hydrogen bonded clusters. Then we also identified the ice-like particles on the surface, and we actually used the point net that we had developed to do this, because that really helped us identify across many different ice structures rather than just focused on hexagonal or cubic, which is what the traditional autoparameters do. And that really did help us identify a lot of the ice molecules that we would not have seen otherwise. And in a few slides, I'll tell you why that was actually exciting and an interesting thing. Anyway, so you can see that the hydrogen bond clusters are formed in this bare mica, and those regions where you have those hydrogen bond clusters on the bare mica, you also see these ice-like particles, right? So that's telling us that the bare mica surface of those regions devoid of ions promote the cluster formation and ice-like configuration. So that sort of together, if I put the 2 points I told you earlier and this together, helps give us an idea of what's happening with this mica surface for ice nucleation. And very we were very excited when Patev published a paper recently where they ran microsecond long simulations of water on K plus mica as well as bare mica. And indeed, they found that bare mica is what nucleated ice, and they didn't see any ice formation on K plus mica. But in addition, on the bare mica, they found a very interesting ice structure form. It wasn't cubic or hexagonal, it was a stacking disordered ice, and it was at a very interesting angle relative to the surface. And that would have been very hard to identify if we were not using PointNet, in the sense of those early ice nucleating or these ice particles that we saw, I think relate to this phenomena that they saw very interesting structure. And we'll look into it further then. So that tells us, I'm sorry about that. So that essentially tells us how we can synergistically combine these experiments and simulations to really delve into depths of what's happening for heterogeneous ice nucleation. So now if I put all of these results together, the earlier AGI results, kaolinite results, and muscovite, or the mica results, the key take-home message that we see is that it's the metastable liquid water near the surfaces that has signatures that can enable us to predict ice nucleation. So we really want to now go further and see what are these signatures that are good predictors for ice nucleation, right? So to do that, the main question is, can we use this metastable liquid water structure to predict ice nucleation propensity? But to do that, we need some cheap way to sample nucleation. We can't run many long simulations. We also can't do advanced sampling on all of these different surfaces that we want to study, right? So we thought a lot about it, and then we developed this rigid seeding method, which really was motivated by the beautiful work from Vega's group and Peter's group on seeding in homogeneous systems. Tarak, how much time do I have?
I think more than 10 minutes.
Oh, okay, so I have a lot of time. I think I went too fast. Okay. So what the seeding method does essentially is at any given temperature, you put in a solid seed of the crystal that you're trying to nucleate, and you put different sizes of that seed, and then you just run simulations of it. And what you'll see is if the seed is smaller than the critical size in the course of the simulation, the seed size will decrease, essentially the crystal will dissolve. If it's larger than the critical size, it will continue to grow. And then if it is at the critical nucleus size, then you'll see some that will grow and some that will dissolve and others that stay. So pretty much this should be a 50-50, right? And then if you assume classical nucleation theory and you use this critical nucleus size, you can back calculate the nucleation rate for the system. And I'm showing you an example of something like that Vega's group has done, where they're looking at the nucleation rate for ice using different water models and at many different supercoolings. And really you can see that they can span a huge order of magnitude here. Some other disadvantages here are that you do assume what the bulk structure of the nucleus needs to be. And this method, especially the nucleation rate, will be sensitive to the definition of the nucleus. So you have to just keep these in mind when you're using this method and calculating the rates. But the recent work from Vega and others have shown that the seeding method actually has shown very good agreement with other techniques such as FFS, umbrella sampling, etc. So it's quite remarkable that it works as well as it does. So now if you want to extend this seeding method to a heterogeneous system, you need to think about multiple factors, right? So one, you have to identify which crystalline plane will be in contact with the surface. So all crystals, and I'll use example of ice, have many, many different planes. So you have this prismatic plane, you have the basal plane, you have the secondary prismatic plane. Which one of these will be in contact with the surface is not known a priori. And then once you have the crystal in contact with the surface, it'll also have some orientation relative to the surface normal. So what that orientation has to be is also not known a priori. And then it's almost never the case that you have the surface and then ice on top of it. You always have an intermediate layer between them, which is, I like to call it being somewhere between the liquid and the solid phase, right? And this was also seen, and Amish also touched a little bit about this on the disordered structure that they saw in contact with the surface. So what that layer looks like and how thick should that layer be is also not known a priori. So when you're thinking about developing a method, all of these things have to be taken care of. So in our method, this is all of the things that we are able to do. And so this is what the method looks like. So we take a surface, we put a box of water over it, we run a simulation, and then we cut an interfacial layer. This interfacial layer is typically the first hydration layer of the water molecules, and you can take a thicker layer if you want. And then we place a seed of ice, and now we can place many different seeds, and that's what we do. And these different seeds essentially are different ice structures. So you have hexagonal and cubic. You can also do other structures if you want, including stacking disorder. And then we also do it such that different planes are exposed to the surface. So what these snapshots are showing you is that first layer of ice that's in contact with that water layer, right? And then we keep the seed rigid. We do it through adding, bonds and angle potential, but basically it moves as one body in this stage. Then we place water around it. We energy minimize it, and then we equilibrate it at some temperature, and then we anneal it to whatever temperature we are interested in studying. And at this stage, the seed is still rigid. And then at the last step, we release all the constraints of the seed, so it's no longer rigid, and we just run an unbiased simulation. And we see what happens to that seed as a function of time. And depending on the size of the seed, it might dissolve or it might grow. And then that tells us what the critical nucleus size is, and that tells us then which type of ice wants to grow on the surface, on which plane, and which orientation, etc. So I'm showing you very quickly some of the results that we got. So here I'm showing you rigid seeding on self-assembled monolayers, and the terminal group is a carboxylic group, so it's COH group. And we see that, and I'm showing you the profile as a function of time of the cluster size for these different planes, right? So you see that the cubic ice pretty much dissolve. This hexagonal 100 dissolves, this 110 hexagonal dissolves. So none of these form on the surface. But you see the IC111 grows and this IH001 grows. So that tells us that it's either this or both that are favored by the surface. Now, if you look more closely and observe the trajectories, turns out that these seeds where we had the IC001 in the beginning, they actually in the course of the whole process tilt. So they become something like this. And when they tilt, they expose, in fact, the 111 surface, and then they grow. So this collectively tells us that it's the IC111 that is favored by this COH surface, and that's the ice that grows. We also looked at kaolinite surface, and we can tell which ice grows, but all I want to highlight here is that we get the orientation also correctly. So here you're seeing the seed, and I forget, I think this is cubic hexagonal ice. And you see that it's supposed to be at an angle relative to the surface, and that angle is captured well with the seed. So this is what our seeding shows. And then in this darker blue is what you get from MD simulations, and you can see that the agreement is quite good. Now, based on this, you can find the critical nucleus size. And based on that critical nucleus size, making the assumption of classical nucleation theory and doing a little bit of other approximations, you can actually calculate the nucleation rate of these systems as well. So then this tells us that this method allows us to identify the crystalline plane that should be in contact with the surface. We can identify the orientation of the ice crystal relative to the surface, and we're also able to sample the different variations between that has to be in the that variations possible in the contact between ice and surface. And what is really interesting is if we try this without that interfacial layer of water, liquid water, you will not get the right results. In fact, most likely we don't see any ice growing. So that interfacial liquid water is actually really important, and it's essentially what helps bridge the surface with the ice. And that layer essentially, I think, is where the molecular signature of ice propensity is. All right. So now once we have this method, you can imagine that we can calculation nucleation rate at various different surfaces and use machine learning like techniques, where we use for doing both identifying what surface properties correlate or can predict the ice nucleation rates, but we can also then use it to develop new surfaces and try and do designing of surfaces that both inhibit or promote ice nucleation, depending on the application one is interested in. With that, let me acknowledge the students who actually did this work. So all of the Mica work I showed you was done through a collaboration with Will Cantrell and me, and the students were Nirunhad Lata, who did all the experiments, and then Joe did all of the simulation work. For the R seeding, Joe and Tim did all of the work. Tim actually developed the method, and then Joe helped with further calculations. Both of this work was funded by NSF, and I was at Clemson before I moved to UMN, so it's the Clemson supercomputer where all of these calculations were done. With that, I will be happy to answer any questions. And I also wanted to just, advertise, I guess, the STMS virtual seminar series that I've been organizing with my colleague Amir Haji Akbari at Yale. This is, a seminar series that's focused on talks on stat thermo and molecular simulations. I think it would be relevant to many of the students in the audience here. We usually have it on last 2 Fridays of each month. And here is the website you can go to see the schedule. We have a really exciting for spring lineup. And I think so far the talks have been really good. So I think they'll be very useful to many of the people here. With that, I will stop talking and I'll be happy to take any questions.
Thank you, Sapna, for a fantastic talk. Many things that I learned from your slides, especially the rigid seeding. Thank you again. Let me take a few questions from the chat box. And Jagannath, would you like to ask your question to yourself, or?
Yeah, I think so. Swapna, very fantastic presentation, and I really loved your slides. So what I really wanted to ask is that I think near the end you kind of talked about it. So at the very beginning when you're talking about this Mica surface, do you basically think that the plane indices of the surface might play a role on the adsorption of the ions, and especially the sodium versus calcium ion? And is there a
Yeah, so that's a really good question, right? So I don't know if the Miller indices per se will play a role, especially in case of Mica, because they're quite clear which plane has the ions, but the adsorption sites of the different ions on the surface are different. And it's really a balance of the ion water, ion surface, and ion surface interactions. Ion surface, water surface, and ion water interactions. So we've been actually doing some work that combines DFT and MD simulations to see what are the preferred adsorption sites for these different ions and why, because it does play a role in sort of guiding the interfacial structure of water, right? Because in some cases, the ions go sit in the cavities on the surface very well. In the others, like calcium and magnesium, they like to be above such that they're almost fully hydrated. Okay. So that would make a difference. Now, in other mineral surfaces, the ions aren't involved in this manner, but there, the Miller indices do matter. It really depends on what plane is exposed to water. And in fact, when you have etches or you have scratches, like some other plane gets exposed, and that could be a better nucleator. So then that becomes this defect site. So, and that becomes really hard in many cases for experiments, because experiments just crush the mineral and then study ice nucleation. So you have everything exposed. So that's a little bit tricky. So the way I envision eventually, making use of this is the experimentalists have to figure out how they're going to characterize the interfacial structure. And then that we can feed into a prediction tool, because the bottom line is the interfacial structure matters. But they don't have a way of characterizing that yet. I mean, they do use SFG, but they get contradictory results. So that's for the experimenters to figure out.
Okay, thank you. Yeah, thank you for a very clear talk, actually.
Yeah, thanks.
So the next question is from Gaurav. And would you like to ask your question? Or you want me to read it out? So can your observations on effect of ions on water nucleation be correlated with the Hofmeister series, that is the ability to salt in and salt out proteins? So
Gaurav, I say 20, 30, 40, 100 miles away from Hofmeister series. So we did think about this. A reviewer also asked about this. But the fact is that you can almost make everything and anything fit to Hofmeister series in a weird kind of manner. So we really didn't jump to that and say that we can see a correlation. I would think to really build one, we would have to study a variety of other surfaces, including, say, not surfaces, ions, including a few molecular ions to really make a conclusive statement. So we've stayed kind of away from making that correlation just based on the results we have so far.
Okay, so the next one from Andre. Would you like to ask your question, Andre? Or,
yes, thank you.
Yeah,
thank you for the exciting talk. I learned a lot. And coming from an electrochemistry background, I thought whether you may have considered a comparison between cations of the same charge, but varying structural entropy of solvation. So structure making versus structure breaking trends among the ions.
So would I do this simply by changing the size of the ion essentially, or is there other ways that I could do it?
This is not just the size of the ion, but the most closely related to the size of the solvation shell around the ion. Typically, these are measurable as the change of electrochemical potential versus temperature, which is a sign of the entropy of solvation.
Okay, so we have not thought about it in that terms. We have looked at the change of size, but that doesn't make much of a difference, especially I think because of the role of bare mica, right? So ultimately it's just depending on trying to make as much open space as you can make. So that's where the valency sort of comes in. If I had to like really make a semi, bettable guess, then I would say that probably cases where the solvation shells are not too tight would be better, because then the water can reorient and sort of accommodate the salt and the ice structure, right? But I have not thought about it in terms of structural entropy or how I would change that in my simulations with keeping the valency the same, but not changing in other ways than changing the size, right? Like the only thing I can think of is changing the size.
Okay.
Yeah, it's a comparison like lithium, sodium, potassium, something like that.
Okay. Yeah, we can. Yeah, so that I think of as changing sizes, and we can definitely do that. That has been something that I've been asked a lot, but I've not necessarily done it. Yeah, we do have some data on it, but we haven't like looked at it from that perspective yet. But it might be an interesting dimension to explore for sure.
Thank you for your answer and for your talk.
Thanks, Andre. So the next question is from Amish, and he asked, do you always choose the ice seed to be hemisphere, or do you also vary the shape, or you take
Yeah, so that's a good question, right? So in case of these surfaces that we've done so far, we've mostly done like good nucleators, so to say. So using a hemisphere works. But when you start thinking of a poor nucleator, hemisphere may not always work. So we have tried using different shapes. We essentially try and change the contact angle a little bit, or try to make it a bit bigger or smaller, in terms of the stacking. But the other advantage of rigid seeding is because that initial seed is rigid, and we do an annealing process and let it run at a lower temperature, if the seed wants to grow and it wants to grow in a certain funny shape, it can, and it has. In fact, we've done this on mica, and it did grow in like a funny shape. And initially we thought, oh my God, why is it doing this? Something is not right. But after Pate's result, we said, oh, it was actually telling us something sensible. We just didn't know how to read it, right? So I think even though we start with the hemisphere, it doesn't have to stay that way. It can sample whatever it wants to sample.
Okay. So yeah, I think we're done with these questions from the chat box. And let me thank you again, Sapna, for a fantastic talk. And I think we have 2-3 minutes for a coffee break, quick coffee break. Organizers?
Yes, yeah.
Yeah, and then we'll be back here on
so much
at 9:20.
all the speakers, yes. I'm already having my tea.
Okay, great. So see you in a couple of minutes.
Yes. Thanks, Sapna. So you'll be there for the next RARE, right?
Yes, I'll stay. You know, it's funny because my sleeping time is like between 8 and 9. I sleep at 8 or 9 and I wake up at 2 or 3. So
No, I think Nishant meant that whether you will be there for the next rare.
I mean,
next rare. Oh, sorry. Yeah, if you invite me,
maybe. Of course,
if you invite me, I mean, you went to Agra and Jaipur, you know, I am from Jaipur. So I was like, oh my God, you guys were right there.
We didn't go to Jaipur though, actually. It was under the plan, but it got, yeah.
Oh, someone said
Jaipur,
like last time one of your rares was in Jaipur, wasn't it?
no, first one was in Kerala.
Okay, yeah, this one, yeah.
And yeah, so, and the second was was supposed to be in Jaipur, but then we moved to Agra.
Oh, I see. Okay.
Yeah.
You know, in fact, it's funny because this is the one which we started thinking about it like 2 years ago, right? This is the one for which I said, can I bring my mom along?
Yes, yes.
After that, you
And
guys
Nishant, you are streaming this also.
Oh,
You're
okay.
live streaming this also.
We totally are.
I think Chris Jarzinski, who helped organize the last one, he was very excited to take a hot air balloon ride in Jaipur right before the meeting.
Yes.
Oh. Yeah, you know,
Incredible.
I mean, no bias, but I think Jaipur is awesome.
Yes, sure, yeah. No, only due to logistical issues we moved to Agra. Actually, it was.
Agra is good too.
Yes, yeah. We were not completely sure about the
Ghats, I think, right?
Yeah, it was, the weather was very unpredictable. We had like early fogs and yeah, so we thought at least Agra is closer to Delhi and we can somehow manage.
I see. Okay.
Otherwise, another flight to Jaipur is too risky.
Right. Yeah. Oh, yeah. So I never fly from Delhi to Jaipur. I take that nice 6-hour drive.
Right. Yeah.
Yeah. So
we can.
Shall we start?
Yeah, I think we can start. Yes. Yeah.
Okay. So Navjeet, are you there?
Hello, I'm audible?
Yes,
Navjeet. Yeah.
Great. So we have our next speaker, Navjeet, and he's, I think, assistant professor in Haryana. Yes. And so today Haryana University is an assistant professor, and today he'll be talking about protein ligand binding through the lens of machine learning. So I think we're going to have another exciting machine learning talk, and so we're looking forward to it. Navjeet, please go ahead and start your presentation.
Is it visible?
Yes, it's clearly visible and audible.
Thank you, Tarak. And I would like to thank organizers for inviting me and giving me an opportunity to present in this big platform. I will be talking about very focused problem, and it is very interesting also and very crucial also, because all the simulations data when we used, they all depend on collective variable, and we have discussed in this rare meet also that there are different ways how you achieve these collective variable to get the different properties. So as previously we have shown that one can achieve the binding of ligand if you start from the bulk solvent. You place your ligand in the bulk solvent. We have shown here benzene, putting a benzene in the bulk solvent, and it finally diffuse throughout the solvent, then diffuse at the surface, and finally bound the final binding pose. So this one we have done using just GPU based machine, and we simulated very long simulation, completely unbiased way. So this was the one system, T4 lysozyme, and we shown the benzene binding to the cavity, which is very deeply buried. Another system which we have simulated was the camphor binding protein, that is cytochrome P450. In this system also, we have shown that if you place your ligand in the bulk solvent and allow it to diffuse, and it will slowly go to the intermediate state, and it will wait there, it will try to do some chemistry there, and then slightly finally enter into the binding pocket that is also very deeply buried. And we have not just run one long simulations, we have run very long multiple simulations, and we have achieved very interesting events in these simulations. As we can see that in the top figure A, we can see that the 3 multiple trajectories. In all 3 trajectories, cytochrome P450, when it binds, when CAM binds to cytochrome 50, there is a very long intermediate states, and then it is a final bound state, which is very close to the crystal structure. Similarly, we have shown that when you have this T4 lysozyme, it also has similar binding events, but there are interestingly different kind of intermediate states. Some are very fast binding, some medium time events which wait for some time, then enter into the binding site, and then there are long binding events also, where the ligand waits a long time and then enter into the final binding site. But in case of cytochrome P50, there is only a single dominant pathway, but in case of T4 lysozyme, we have multiple binding pathways there. So we have used a good CV there, and with using that very good CV, we have achieved very excellent results in the terms of binding kinetics, thermodynamics, where we have shown that the kinetics of binding and unbinding is very close to the experimental values, and they are in excellent agreement for P450 CAM also. And we have also shown that if you have T4 lysozyme, you have multiple binding pathways, still you achieve very good kinetics using computer simulations in an unbiased way. K1 and K off was very good in good was in excellent agreement with the experimental values. And we also have achieved the many binding pathways in case of T4 lysozyme, and we have shown that how they are connected to each other, how they interconvert to one metastable state to another metastable state. But in case of cytochrome P450, we have shown there is only single dominant pathways, and it always prefer that only, and it follow the same trend in all 3 trajectories. But there was some few problems which we were not able to solve with this very good CVs. So what was the things which we did not achieve using this very excellent CVs was how protein conformational plasticity is regulating the ligand binding. Means we can see that okay, ligand is going and it's waiting, it's entering into the pocket, there are multiple pathways, but we did not able to get that how this protein is acting on the ligand. Is this their protein conformation which are playing a crucial role for ligand to select its final bound states, or ligand is just only the trigger point for the binding of the final bound state? So we try to understand what may be the issues there when we try to use protein plasticity with ligand binding. So the major issue was that when we use an automated method which use a CV generation protocol, and if we combine the protein plasticity with the ligand binding, we have seen that the bound state and unbound state not getting separated. Means protein conformations always getting some states of bound state, some are unbound state. There was a mixing of bound and unbound states. So we tried to look into that, what may be the reason. So we propose that there may be 2 reasons. One is there may be time scale difference, means dynamical time is too disparate in both events. As you can see, and in this trajectory, I have shown a schematic there. We can map the trajectory into different states. Each frame is mapped like 1, 1, 2, 2, 2, 3, 3. And we can see that 3 state is having unbound state also and bound state also if we put the ligand state on that conformation. But another maybe reason that we have too much fluctuations in the protein which are hindering the separation of the events, which are not able to separate the unbound to bound state in the protein conformation. So if we use a new CV with less noise, it may separate out like 3 prime states will become from 3, and there will be no mixing of the states. So as we know that machine learning is getting very popular these days, we try to look into that. Can we solve this problem using machine learning approach? So we want to solve that protein conformational plasticity should be get separated during ligand binding. So we have used 2 systems. In one system, we have induced feed mechanism. Induced feed mechanism is what? Like ligand is coming to the intermediate state, and it is ligand is inducing the conformational change, like it is placing some side chains and then entering into the pocket, and then final achieving the binding steps, like it's getting into the final binding site. In another case, we have T4 lysozyme. T4 lysozyme has multiple binding pathways, and ligand has different way of entering into the pocket, but we can say that this is following the conformational selection. Means protein already have the pre-existing conformation which is required for the binding of the ligand. So to understand it, that what may be the problem if we use the just protein conformations to get the CV, final CV, and look into this how ligand is positioned on the top of it. So we have used very standard procedure here. The standard procedure is that we have the residue distance, which is a protein conformational plasticity like features. And in this residue distance matrix is used as the input CV. Then we have used a very standard protocol which for dimensional reduction technique like time structure independent component analysis. And we have obtained the slowest dimensions, and we projected our trajectory on those first two slowest dimensions. And to understand the ligand positions on the top of the surface, we color the surface according to the distance of ligand from the cavity. Like you can see, the bound is, these are three trajectories projected on this slowest tick 1 and tick 2, dimension 1 and dimension 2. And the blue color is representing the ligand inside the pocket. And when you see the red color, it is a unbound state completely in the bulk side. So as one can see that in these all three trajectories, the blue surface or blue side, binding side is completely separated. There is no mixing, and other states are separated from the binding events. So when we have shown that in induced fit mechanism, there is clear separation between the bound and unbound state. It means whatever CV we are using, and we are using just protein conformations to get our input CV, and the bound states and unbound state getting clearly separated even without considering the ligand positions there. But as soon as we move to another system, that is benzene binding to T4 lysozyme, this benzene has multiple pathways of binding. It has conformation selection model, and we follow the same exercise. Like we have input CV as a residue distances, native contact featureizer. We have used a time structure independent component analysis as a dimensional reduction techniques. We projected each trajectory along the slow dimensions, first two slow dimensions. We color the surface according to the ligand distance from the binding site. Like this is the surface of trajectory 1 for trajectory 2 and trajectory 3. All these trajectories are colored according to the distance from the ligand. Like bound is blue and red is unbound. If you see all three trajectories, they have different kind of behavior. Trajectory 1, there is no blue on the surface, completely red, means like all the bound conformations are scattered throughout the surface. But if you look in the second trajectory, it has slight blue, but very light blue. It means it's going more than 10 angstrom distance. And then it's showing that, okay, these conformations are distributed, but not very clustered at one place. Trajectory 3 get very clear separation. Means bound state and unbound states are completely separated. So we have proposed two methods that, okay, there may be two reasons for this. One is there are different time scales. Time scales are completely different due to events. To nullify it or to test it, we have compared the implied time scales of two events. One time implied time scales for ligand binding, when we are considering ligand going from bulk to the solvent, and another is a protein plasticity only. As one can compare these two time scales, we can say they are not very different. We can compare them. So there is a time scale is not the main cause which is causing the mixing of these events. So how to solve this one? So it means there is a noise in our data which are hindering our separation of mixed and bound state. So we have standard procedure in which we have residue distances as input CV. We use the demonstration technique, time structure independent component analysis, and we project our surface trajectory on the slowest dimension. In our procedure, what we have used, okay, instead of this going from directly input to input CV to this dimension reduction, we add another layer of supervised machine learning. In supervised machine learning, what we are doing, we are providing the ligand positions to the CVs and trying to identify, okay, which residue pairs are crucial for the binding of this ligand. So for this purpose, we have used random forest classifier, and from this random forest classifier, we have used feature selection approach. So what is random forest approach? In random forest is a supervised machine learning approach which uses a decision tree, and it generates an ensemble of decision trees using bootstrap methods. It selects the samples from the original input series and generate the multiple trees. And these from multiple trees, it finally generate the final model and give us the classification of bound and unbound states. So what are the advantages of this method? First, we can choose the descriptors which are decisive factor to classifications. Another, there is no overfitting in this method because we are using a voting method and we not just bias to one or one matrix or another matrix. Second is it's very easy to train. We can interpret it very easily. There's no black box in this. So we have our standard procedure. We have added one layer, that is random forest classifier feature selection. So in random forest, what we are doing, we have trajectory data. From 3 trajectories, we have residue pairs. Here x1, capital X1, capital X2, capital X3 to capital Xn. So we have total n number of residue pairs, and these residue pairs are having distances between during trajectory. So x1, 2, 3, 4, m is the number of frames. When we combine all 3 trajectories, we generated a matrix. And we label each frame with bound or unbound using distance criteria. If this is close to the pocket, it is bound. If it is not close to pocket, it is unbound. Then we provided these input features to the random forest classifier. It did bootstrapping, it generated the samples, it did decision trees, then generated some trees, and from the trees voting, it got the final model. In this process, it also provides the score to features, like the importance of each features in the model. So we can use this importance score, which is we obtained using Gini method, to select the pairs which are crucial for binding. So we have used loop cumulative score of these importance of features, and we've identified there is a 200 residue pairs out of almost 800 pairs, which are necessary for this ligand binding only. And as you can see, the previously which we have shown, so I'm just again revising my this previously. As we have used standard procedure, in standard procedure we have this Tika surface. In each Tika surface we have color according to this ligand distance. If blue is bound, means either conformations belonging to that bin is blue, it means that the states belonging to that particular bin is bound. And if it is red, it means they are unbound. So when we use a standard procedure, we've identified that the standard procedure did not separated the bound and unbound state in trajectory 1. In trajectory 2, there was a mixing of states, like blue becoming to the cyan color or blue color, light blue color. It means there is a mixing of conformations here. But in trajectory 3, we have the separation of events, like we have bound state separate, unbound state separate. But as soon as we use the random forest algorithm, we use input features, we provided to random forest classifier. From the random forest classifier, we calculated the feature score using this ensemble of trees, and we have selected 200 residue pairs which were having good cumulative scores. And these 200 residue pairs we have again provided to the Tika dimensions or Tika dimensionalization techniques, that is time structure independent component analysis. And when we obtain it, we can clearly see that the trajectory 1 along tick 1 and tick 2 has separation of events. Like previously there was a mixing, now there is no mixing in the events. Blue color is getting completely separated from the red states. Means the conformation which was getting not separated from the bound and unbound states, now it's clearly separated. Similarly in trajectory 2, there is, in the previous we were having a light blue color. Now the dark blue color is completely separated and is clustered in the same place only. In trajectory 3, we already get separation, but now in this case, when we use random forest, we still get the separation, but better way. Like it improved the previously whatever noise was there. So another question comes, okay, what are these residues in this process which we got good feature score? So for that one, what we did, we projected these residue pairs on the top of protein surface. And we have shown these residue in the sphere form and the connection residue distances in the form of bond. So as one can see that there are two domains, C domain where the ligand binds and N domain which is very far away from it. So the residue which when we projected on the surface are not clustered in the binding site only. So they are not just residue which are involved in the binding, they are scattered throughout the surface. So it means it's not just residue belonging to the binding site which is causing the binding to the, or which is classifying the binding site, binding events. When we want to compare, okay, if we have three different trajectories and if three different trajectories shows different binding pathways, is any their role of these different kind of networks? So what we did, we have unbound state ensemble and bound state ensemble on the Tika surface. So what we did, we selected some conformations, representative conformation from unbound state and some representative conformation from bound state. And what we did, we calculated the change in the fluctuations, like if going from unbound to bound, what is happening to that bond or connections. And we projected this change in fluctuations on this 3D surface to see, okay, which residue pair got affected for three different trajectories. When we compare these three different trajectories, we found that even though in the trajectory 1, ligand binds from H4, H6, where this I have shown binding site arrow, these residues are not getting much affected, but the residue which is very far away from the site is getting large conformational changes. Means the motions of these residues which are very far away are responsible for H4 or H6 binding pathways. In case of second trajectory, we've seen that on the binding site, where we have seen more large conformational changes. In this case, ligand binds from H7 or H9 helices. So these two trajectories are showing different kind of pattern of the fluctuation in the residue pair which we have selected from random forest methods. But in trajectory 3, where we have seen that there is no change if you use random forest method or not, or without random forest method. So what we see that there is a conformational change in the all residue pairs are minimal, means that there is similar kind of pattern of fluctuations using random forest and without random forest. It means these all residue have same kind of contributions throughout the trajectories. So it's not the only thing which we can see that from this analysis. What we can see that the classifier has predicted residues, and these residues are in position which is allosteric site, means they are very far away from the distant site. And when we compare these residues, we found that there are residues 18, 22, 137, which is showing very thick change in the conformations or a thick bond. These residues has been reported previously in this T4 lysozyme that they play a crucial role in the protein and ligand binding and the hinge motions which allow it to the breathing motions to this protein also, and which help us these ligands protein to allow ligand to enter into the pocket. So these all three residues have multiple residue pairs in this N-terminal domain, so that they can control the breathing motions of this whole protein, so that ligand get the chance to enter into the pocket. So what we have learned from all this exercise, that we have proposed a method which can easily remove the noise from the trajectory data, which shows that if you use automated method to get the to separate out the bound and bound state from the conformational ensemble, you can remove the noise using random forest method, which is supervised method to separate out the noise from the unbound to bound ensemble. Another thing, what we have learned, that if there is an induced fit mechanism where ligand is changing the conformational change to the protein, then there is no need to use any machine learning approach. The standard approach, that is linear approach, is sufficient to resolve the protein conformational plasticity and ligand binding. So if you have conformation selection, then it's better to remove the noise before going to the final any demonstration technique. You just select a subset of residue, and if you have induced fit mechanism, you don't need any random forest or any supervised or any machine learning approach. Linear techniques are sufficient to separate those events. We also have observed that there are residues which are not close binding sites, they are allosteric sites, which also play a crucial role in the protein ligand binding and protein conformational changes. I would like to acknowledge my mentor, postdoc mentor, Dr. Jagannath Mandal, who has provided me a very good guidance during these projects. And I would like to acknowledge the resources of TFR Hyderabad Computing Facility, where all the work has been carried out. Thank you.
Okay. So thank you very much, Namjeet. It was a wonderful talk. And before anyone starts typing questions, let me ask you a couple of questions.
Yes.
I'm curious, rather.
Yes, sure.
Yeah. So you talked about starting from this residue contacts, you do one level of filtering by using this random forest, and then you feed these things to the Tika.
We have selected the subset of the residue pairs.
Okay. Yes.
So we have suppose n residue pairs, which has some non-relevant pairs.
True.
So what you do, just you remove some of the pairs which are not relevant for the binding events.
For that, you are using the random forest.
So we are using supervised method so that we select the residue pairs which are necessary for the protein conformational chain and ligand binding. Okay. And then we use this linear approach, time structure independent compound analysis, so that we can add the time also, and we get a time separated conformations which are not bound and unbound together.
Okay, so in this random forest classifier case, you get the ways for the residue contacts, and thus you can remove them as noise.
What?
So from this random forest classifier, you can kind of find out those features which have a lot of weight.
We get feature score for each variable, like, and you select the top features according to that weight. Hello?
Am I audible?
Yes, sir. Yes.
Okay. So in the Tika analysis, I guess you ran few simulations, right? Unbinding events.
No. We have already simulated data, binding data already. We want to get the analysis of that binding events, because you cannot get just one CV is not giving all the results. Like when we got the binding kinetics and pathways, we missed the protein conformational plasticity.
Okay, so you have multiple unbinding events trajectories, right?
We have multiple trajectories for the binding events, like independent binding event trajectories.
Okay, so now one thing that comes to my mind, so do you think this CV, the collective variable that you used, might impact your time of unbinding?
No. It's just if you shuffle when we are using this random forest, it's take the subset from the conformation. So it's not just taking time events there. It's just a random conformation is selecting which are labeled according to the bounded and bound events.
I see.
And then building the trees, so get the decision it can take.
I see. And these unbinding trajectories that you generate, those are biased, or?
I did not consider unbinding trajectory here. For MSM, we considered that only. Here we have considered only the trajectories which were having complete reaction cycle, like going from unbound to complete bound events.
I see. The last one, in one of your slides, I saw the unbound state is a bit deeper than the bound state. Probably, yeah, that one or the next one. Yeah, this one, yeah. No,
this one.
Previous one, the first Tika 1, Tika 2 plot. Is there something that the ligand is getting stabilized in the solvent?
Unbound state.
Yeah.
This is actually in this CV, I have not considered ligand positions. It's a protein conformational plasticity only.
Okay.
I have considered input CV, which is having only residue distances.
Okay.
And ligand is not present in this CV. So the conformational has some different kind of ensemble. and they have some favorable conformations, some are unfavorable.
Yeah,
and unbinding is based on I have mapped the binding events on these conformations.
Okay, in that, yeah. So that makes sense because the protein is getting ready to bind the ligand probably. That's why.
So we'd like to identify that which conformations are available for ligand binding and how they are interchanging to each other. I mean, what are the time scales and how they get. So when you do clustering and you want to build a model, you need to separate these bind and unbound events. Otherwise, you will get that same events was having bound events and same conformation was having unbound events. So you will not be able to interpret. Either you will do manual separation of these two events, or you will get the mixing of the events. Like you will not be able to get the one answer at the same time. Either you miss the binding or you miss the protein plasticity.
That's true. Thanks. There's one question from the chat box from Sudarshan, and he is saying that I was wondering if RF classifier, random forest classifier will be useful for biased trajectories as well.
One can use biased trajectories also, because we are not using time profile here. Because in all these analysis, we have used time profile only in time structure independent component analysis when we reduce the dimensions. But to train your system, you just need conformations which are labeled with bound and unbound events. In this approach, you can identify which residue pairs are crucial for the particular two different kind of events. Classifying the events based on supervised learning only. And our main objective was we should add the supervised learning when we have too much noise in our system.
Yeah, so thanks. The last one quick one. Somebody is asking how long these trajectories are. And in case of protein ligand unbinding, the conformational plasticity, they take place in millisecond time scale. So would you like to comment on this? So how long the trajectories are?
They are microsecond long trajectories.
Microsecond, okay. So he's saying that sometimes it takes milliseconds to see these conformational transitions. But anyway, I think for that you need to run on bias simulations.
No, for that one has to go for the Markov-State model.
Markov-State modeling, yes.
It's just to get the pairs which are necessary for this, to separate these or which are responsible for binding. And then you can generate this Markov-State model from that one, and you can calculate the protein kinetics also from there.
And in fact, one can run biased simulations and then do this stick analysis, provided you have to take care of these weights that generate bias.
Yes.
Okay, then. Suman, Dr. Suman has a question, so please go ahead.
Okay, Navjeet, really nice talk, and actually you have made a few of my slides redundant. Thanks for that. But anyway, so I had two kind of clarifications. One is that what is your binding coordinate here? How you're characterizing the binding and unbinding?
I have used the distance criteria from the pocket.
Okay, and then since you are looking at the coupling bit, so can we look at when you are looking at the coupling between the binding coordinate and the conformational coordinate? Can we look into that? Which happens first? Is there a time series information
No, that's the main objective of this one. That if you say that okay, time scale is different, that's why you are getting mixing of events, or some fluctuations which are not necessary for this dimension reduction techniques, which are hindering this separation. How to remove those parts? So what we use, you have to select a subset of the residue pairs which are only responsible for binding. Then you will not be having the protein conformations which are irrelevant for binding.
Okay. No, I was curious that as the ligand is approaching, so then how the protein is sensing that approach. So then
induced fit mechanism, there is no problem because ligand is changing the conformation chain. So automatically they get separated. But when you have conformational selection, so you have ensemble of conformations, they are fluctuating throughout the time. But all the fluctuations are not relevant for the binding. Some residue pairs are the triggering events, or when ligand will interact the protein, those motions will be dictate the ligand binding to that one. So we need to identify those residue motions which are dictating the ligand binding when it interacting with the protein circuit, because it is when it is diffusing in the water, these protein motions are irrelevant to that ligand.
Yeah. And my second quick question was that when you talked about this allostery, do you have any information about the coupling, that how the binding site to the allosteric site how exactly it propagates? Did you look
it is not a continuous network there, because this is sparse network which has disconnectivity. So you cannot calculate the shortest path from there. If you want to calculate the network pathways, you have to have complete network again, and you have to weight these nodes according to the feature score.
Sure.
Then you can generate the pathways also, because as you can see, there is no connection between N domain and C domain in between. Just only they are going through the hinge only. And in some trajectory they have larger weight, in some trajectory they have lesser weight.
Okay, thank you. Yeah, really nice talk. Nice work.
Okay, so let's move on. I think we have the speaker ready. Our next speaker is Professor Suman Chakraborty, Associate Professor at SN Bose Center, Kolkata. And his team works on computational biophysics and theoretical physical chemistry. And so he'll be talking today about navigating free energy landscape insights from mixing multiple reaction coordinates. And I'm really curious to this part, mixing multiple reaction coordinates. And so, yeah, Sumanda, over to you.
Yeah, thank you, Tarak. I'm just trying to hide this panel.
I think it's not visible from our side.
Yeah, so but it blocks part of there is a this video panel on the right hand side.
Oh, okay, yes, yeah, that
blocks my view. Okay, okay, I think I'll just let it be for the time being. Okay, so first of all, thank you, Tarak, and I must thank all the organizers for first of all putting this event together. It has been really exciting. I have learned a lot of things, and I wish that this event happened before I started many of my works, and so I'll have to rethink many of the stuff that I'm going to present here today, and I'm sure that we'll do a much better job after this conference. So now I kept the title intentionally vague, so there is no specific problem that I'm going to talk about. I didn't mention in the title, and and also I'd like to mention that I'm going to give you more insights or physical ideas that the thoughts or the ideas that we are thinking about, rather than giving details about lots of results, because most of the systems that I'm going to present here, those are kind of half-baked. We are still going through it, but at least I'd like to present ideas. So now the work that I'm going to primarily present today, the major focus of today's talk will be essentially this idea, this rational design strategy for allosteric drugs based on some simple thermodynamics principles. So that's the focus that we are going to have, and let's see, we will see as we move along. So the major focus of our group has been to understand the general mechanism of biomolecular recognition and signaling processes. And as we have heard several talks dealing with such systems, even Navjeet presented a few talks, very interesting results related to this idea. So essentially, all of our perception, sensory perception processes, they involve activation of some protein or other. Most celebrated protein is GPCR. It may be activated by ligand binding or light-induced processes. And then when these proteins are activated, they will further activate some downstream proteins and so on. So one major focus of our group is to try to understand how these proteins talk to each other. What is the language spoken by the proteins in terms of the interactions and dynamics, so to say. So now, so essentially, when we talk about a mechanism of signal transduction, we can break it down into two major components. One is the inter-protein signal transfer, where it will involve first molecular recognition. The protein has to recognize its partner, there has to be a selectivity, and then it has to pass on the information. So once one protein is activated, it has to recognize its partner and then pass on this information. So we would like to understand that what is the molecular basis of this information and how does it pass on this information. That is something we are interested in. And then there is another interesting mode of communication, which is allostery. We have heard a lot about it. So essentially that would mean that when the information arrives on one end of the protein, how that information propagates or flows through the interior of the protein and it does something somewhere else. So essentially today, whatever the topics that we're going to talk about, we'll briefly cover concepts from all of these ideas. So essentially, so let's first establish a molecular thermodynamic basis of such signaling processes. So one standard example of such activated processes is our vision processes, the photoactivated processes in our retina. So essentially, there is a protein called rhodopsin, which has a chromophore called retinal, and on shining light, on photoexcitation, that retinal undergoes a photoisomerization. For humans, this is at this 11 cis position, this double bond, and for other microbes, there is another double bond, which is in the all trans configuration. So now on shining light, this double bond rotates, it undergoes a cis-trans isomerization. And so once this chromophore rotates, it creates a local stress inside the protein, and that will lead to further conformational change inside the protein. So essentially, the activation mechanism is creating a local energetic stress, and that stress needs to be released by further downstream conformational changes as it moves on along the channel, and it will eventually lead to a channel opening, which will lead to ion translocation or ion pumping. So essentially, the idea is that on shining light, let's say this is the ground state, and on shining light, there is a stability crossover. So if let's say for human, the 11 cis was the stable form in the ground state, but when you shine light, the energy landscape flips, the stability crossover, and maybe the trans becomes more stable, and so it undergoes this photoisomerization, right? So essentially, the idea is that excited state or the part-up state has a different energy landscape or the free energy landscape. So when you introduce a perturbation, the free energy landscape is modulated, there is a stability crossover between the states, and it undergoes a conformational change. So that's the general idea. And this can be generalized even further for any kind of perturbation. So if you think like this, that if you plot free energy as a function of the conformational coordinate, with any arbitrary conformational coordinate, so let's say this is the resting state, and then there is a perturbation, and then in the perturbed or activated state, there is a stability crossover. So in the resting state, this was the global minimum, and when you excite, let's say you are here in the conformational coordinate, and when you excite it, now you are in a metastable state, and then it will flow over to the next, the global minimum has now changed, so it undergoes a conformational change, and when the perturbation is removed, it will come back to this metastable state, and then finally it will come back to the global minimum. So this kind of cycling process would be the hallmark of any kind of signaling processes, be it photo-induced perturbation, it can be binding with ligand or small molecule or protonation change, pH change, and so on. So essentially, in summary, the hallmark of signal propagation or sensing would involve a stability crossover or switching of the conformational landscape. And that's how, this is essentially the molecular thermodynamic basis of any kind of signaling processes on activation. So let's just look at very quickly one particular example that will highlight this aspect. So we have been looking into this sodium pumping KR2 rhodopsin channel eminent protein for a while, and we recently looked into the water dynamics in this protein. I'm not going into the details of that. I just wanted to highlight that in this protein there are several strongly bound water molecules. So along the channel of this protein, there are certain hydration sites which have residence times of several hundreds of nanoseconds. So they are very strongly, there are strongly bound water molecules with possible functional role. But we'll not look into we're not going to talk about so much about water today. But what I would like to highlight here, that as you photo-excite that retinal, essentially the retinal goes from the trans to cis configuration, right? So as you flip this switch on photoexcitation from, let's say, the trans to the cis configuration, there is a gate, a hydrophobic gate that is supposed to open, right? So let's say this is this leucine 120, and that has to get out of the way. It has to rotate like this. So this is the open state. So this hydrophobic gate, when it opens up, the channel opens and the water molecules can pass through. So essentially what we would like to, we wanted to see here, that whether really that stability crossover can be reproduced through the free energy calculations. So essentially what I show here, this is the conformational coordinate of this rotation of this leucine residue, L120. So in the resting state, when it is in this KR2, the resting state, as you can clearly see, the closed conformation has higher stability. So this conformation of this leucine, the hydrophobic gate, has greater stability. But as you flip this switch in the retinal, it undergoes a stability crossover, and then the open state becomes more stable. So essentially, the rotation of this retinal is coupled to the conformational energy landscape of this particular rotation of this particular leucine 120. So this establishes the point that once you create one perturbation, energetic perturbation that modulates the free energy landscape of the downstream response of the protein, that will further undergo further conformational changes along the channel pathway. And another interesting observation from this particular system is, since I mentioned about that possible importance of water, what we find that if we create an artificially dry membrane channel, if we remove the water molecules, it seems the barrier of the transition becomes significantly higher. So in the presence of water, as you can see, this open state is significantly more stable than the closed state. But if you remove the water in the black line, you can see that it's significant. They are almost equally stable, separated by a very large barrier. So the presence of those bound water molecules seems to play a very important functional role, and which can act as lubricant by reducing the barrier, as well as they can even modulate the relative stability between these two states. So, so this is something we are pursuing. This story is not complete. So essentially, two things we wanted to highlight here: that energetic perturbation, which is a photoexcitation here, that leads to a stability crossover in the conformation energy landscape of the protein, and the open state becomes more stable on switching the retinal conformation, and also the presence of these water molecules significantly changes the conformational energy landscape of the protein. So at this point, let's change gear, and we'll talk about the binding processes. This is something that Navjit has already discussed, so I don't need to talk about it. So essentially, these are the holy trinity of the binding mechanism. So one is this lock and key mechanism, where you have a receptor and the ligand just binds as a lock and key mechanism. In the induced hit mechanism, there is first the ligand approaches the protein, and then the local interactions induce some kind of a conformational change. And in the other case, in the conformation selection mechanism, the protein itself can exist in multiple conformation, and the ligand just selects the particular conformation that is binding competent. So now, how do we, in general, how do we distinguish between such mechanistic processes? How do you choose between different mechanisms? So this is one example I just wanted to highlight, that in order to distinguish between such mechanisms, for example, induced hit versus conformation selection, it becomes crucial to mix multiple reaction coordinates. Just having one simple reaction coordinate would not be enough. So for example, here on the y-axis, we have some generic conformational coordinate, x, and on the x-axis, we have a binding coordinate. So now, if we think about it, that let's say this is the globally stable conformation of the protein, this triangular shape. So if it goes along the binding coordinate first, so there is a first binding followed by conformational change, we'll call it the induced hit mechanism. And on the other hand, if the conformational change happens first, followed by the binding, then we'll call it the conformational selection. So this becomes a very useful strategy, that by looking at the coupling between multiple independent reaction coordinates, we'd be able to kind of figure out that which mechanistic process is playing an important role. So this is the kind of a take-home message, that often multiple reaction coordinates are necessary to understand the mechanism. So with that, now let's enter the major. So yeah, so then the question remains that what is this X, what is this conformational coordinate? And there has been lots of discussions in this meeting that how to come up with the reaction coordinate intelligently, starting from chemical intuitions to machine learning based techniques like autoencoders have been discussed a lot in this meeting, and Jagannath has showed really nice examples. So, but in our work, we are going to focus on rather traditional, standard chemical intuition-based reaction coordinates, and hopefully we'll move into more intelligent machine. We'll try to use machine intelligence later on. So now this is our major interest. That the traditional approach for drug designing has been to come up with competitive inhibitors, where essentially you try to come up with molecules which have higher binding affinity compared to its natural substrate. So it will compete with the natural substrate and it will not allow it to bind. But on the other hand, there is an increasing interest in identifying allosteric inhibitors, where the idea is very simple, that you possibly have another binding site far away from the canonical binding site, the substrate binding site, and if such an allosteric inhibitor binds far away from the binding site, it will somehow alter the structure or dynamics at the canonical binding site, and that will reduce the binding affinity of the substrate. So there is an increasing amount of interest in identifying allosteric inhibitors, particularly for those cases where it is not easy to identify a competitive inhibitor. We are going to take up on one such example. And also allosteric inhibitors are known to be more selective, less side effects, and so on and so forth. But this is our kind of major focus in today's talk, that how do we think about a design strategy of coming up with allosteric inhibitors, right? So, so these are the few of the strategies. So first thing is that we need to identify some cryptic sites with distal coupling. What do I mean by cryptic sites? The sites that may not be always open, or they may not be visible in the crystal structure. So they are essentially the excited states of proteins, where some local, there can be some local excitations which will open up some cavities, and that can become a potential target for allosteric drugs. And on the other hand, this is something that we are going to propose, that this simple idea of reversibility from thermodynamics can be utilized to design allosteric inhibitors. So let's now look at the most important slide that I'm going to kind of try to emphasize here. So now let's imagine that this particular protein has this binding site. This is the standard, its substrate that is supposed to bind, and there is another site, let's say this particular site, that can exist in two different shapes. So I'll call it, let's say, square, which is signified by S, and I'll call this one triangle, which is signified by T. So now let's assume that when this other site, which is the allosteric site, is in the square conformation, then the binding affinity is given by this delta GB S. And then when the other site is in the triangular shape, then the binding affinity is delta GB T. So here the basic assumption is that depending on the structure of a distal site, the binding affinity is becoming different. But on the other hand, there are two other kinds of free energies that we can look into, which is the free energy of conformational change. So this is the apo form of the protein, where the ligand is not there. Now this delta G S to T in the apo signifies the free energy cost of this conformational change in going from square to triangle. On the other hand, here also the same free energy of conformational change, but in the hollow form. So in the presence, so we are talking about two conformational free energy change. One is in the apo form, the free energy change at this site, and then in the hollow form, in the presence of the ligand, the free energy change. And we can very simply now create a simple thermodynamic cycle, and we can close it. So essentially, it can be shown very simply, very simple thermodynamics, that this binding free energy in the T state will be greater than, I mean, by greater I mean less negative. So it can be, this one will be less negative or higher in magnitude compared to this, provided the free energy change in the hollow form is greater than the free energy change in this. So essentially, just to summarize here, the take-home message is the free energy of binding will be less favorable in the apo form. So whichever conformation of the protein is more stable in the apo state as compared to the hollow state, that conformation will lead to a lower binding affinity. So essentially, the design strategy is this, that we would like to identify some other distal site of the protein which may exist in two or more different conformations, and that conformation which is more stable in the apo state as compared to the hollow state, if we can somehow stabilize that conformation. So essentially now our objective will be to stabilize this conformation by putting some ligand here. So we'd like to kind of lock this particular conformation on this side, and if we can lock this particular conformation, that will essentially lead to a lower binding affinity at the natural substrate. So this, in a nutshell, this is the design strategy that we are going to use. Okay, so this is the thermodynamic principle that we are going to use for design of allosteric inhibitors. So with this idea in mind, so this is the problem that we are looking at. We are trying to understand that essentially to come up with allosteric inhibitors for lowering your bad cholesterol level, essentially LDL that we all are scared of beyond certain age. So here is the basic idea. So essentially in our liver cells, in hepatocytes, there are these LDL receptors on the cell surface, LDLR, here you can see. So these LDL receptors, they bind these LDL particles essentially, and if once they bind the LDL particles, they are they go inside the cell in this endosome, and then this LDL is decomposed, and then LDLR is recycled to the surface. So this process, this cycle, essentially leads to the decomposition of LDL or consumption of LDL in our body. So we would like to promote this cycle. But on the other hand, it is known that there is another protein called PCSK9. It has a very long name. Name is not important. So this PCSK9 protein, if it binds to this LDLR outside, now this whole complex, PCSK9, LDLR, and LDL, this complex, if it goes inside the hepatocytes, something strange happens, that the whole complex gets decomposed into the lysozyme, and the LDLR is not recycled. So the difference is that in presence of PCSK9, essentially PCSK9 binds to LDLR, this recycling is inhibited. So the LDL level essentially goes up. So essentially the design principle will be that we would like to inhibit this PCSK9 LDLR interaction. So if we can somehow inhibit this pathway, that if we can reduce this PCSK9 LDLR interaction, essentially we would be promoting this pathway of LDL decomposition. So this has been a promising strategy in recent last few years, that people have been targeting this PCSK9 protein. So we would like to basically inhibit this PCSK9 LDLR interaction. So that is one goal. So how do we essentially block this PCSK9 LDLR interaction? So the traditional strategy could have been to come up with competitive inhibitors, but unfortunately, this has very large protein-protein interaction interface. I'm going to show the structure very soon. So it is very difficult to come up with a small molecule competitive inhibitors because it's a very large protein-protein interaction interface. There are certain antibody treatments, but again, antibody treatments are difficult to administer and control. So it will be good to have some small molecule inhibitors for this problem. And so then our ambitious dream is to come up with some small molecule allosteric inhibitors using the design principles that we just discussed. So very quickly, this is the structure of this complex. So this big thing that you see here, this is the PCSK9 protein. It's a multi-domain protein, and this is a small EGFA domain on the LDLR. LDLR is a big protein, but this is the domain, small domain that interacts with the PCSK9 here. So this is the EGFA or the LDLR domain, and our goal would be to reduce this binding affinity with this LDLR or EGFA with the PCSK9. And just note that there are these two loop regions, 166 to 178, and again this 211 to 222. So these two loops will be our promising targets, as I'm going to show you very soon. So now the first question that we would like to understand is that depending on whether the LDLR is there or not, so whether it's in the hollow or in the apostate, with and without this LDLR, whether these loop conformations can exist in different conformational states, and which seems to be it seems to be the case that from the crystal structure, some of these loop conformations are missing. So in the bound state, we don't have a crystal structure of this loop, so we have to model it. But as it turns out, this loop can indeed exist in multiple distinct conformation, and then they don't interchange very easily. So here I'm showing some results from simple molecular dynamic simulations. So depending on the ligand binding state or how you prepare the system, here we are showing the conformational landscape sampled by these two loop regions. And as you can see, so essentially here the conformational space is defined in terms of two RMSDs. So let's say we have these two end structure, and here this is RMSD with respect to one of the clusters, and here is the RMSD with respect to the another cluster. And this is the one standard way of characterizing conformational space of rather disordered regions or these loops. So and you can see that in this conformational landscape, the apoform shows samples of very different regions of the conformational space, and also in the bound state, it samples a very different region of the conformational space. And as you can see here, that these conformations are quite distinct, and they don't within the simulation timescales of a few microseconds. They don't really interchange between these intermediate states very readily, and that obviously that calls for enhanced sampling methods. So first idea is here that there's an extensive conformational heterogeneity or plasticity in the disordered loop regions, and although I call them disordered or structureless, they can indeed exist in very well-defined distinct structures stabilized by certain specific interactions, as I'm going to show you next. So the first question is this: we established that depending on whether the ligand is there or not, the loops conformation. So obviously there is some kind of an allosteric coupling between the ligand binding site and this loop conformation. So there is a kind of a long range coupling between these loops and the binding site. So since remember that our idea was that we would like to stabilize those conformations of the loops that correspond to the apoform of the protein. So essentially we'd like to prove this our hypothesis that if we look at this reversibility, that right now we are showing that depending on the presence of the ligand of this peptide, the loop conformation can change. But on the other hand, our argument of thermodynamic reversibility says that if I now lock, let's say in the absence of the ligand, this conformation is more stable. Now, if I now lock the protein in this particular conformation of the loop somehow by adding some ligand, the hypothesis is that it should be able to reduce the binding affinity of this protein PCSK9 LDLR interaction. Okay, so I'll just now, so that's the idea that that LDLR binding modulates the loop conformations, but can it be utilized the other way around? So I'll just quickly summarize our result without going through much details. So essentially we used standard umbrella sampling kind of free energy calculations first, and we showed that indeed there are multiple metastable intermediate states of the loop region. And interestingly, for each of these loop conformations, you see that from each of these metastable minima, we have extracted these loop conformations. As you can see that from these different minima, I have colored this minima 1, 2, 3, 4 in this way. And then from this minima, if we extract the structures and then compute the protein ligand binding energy, so we have used some simple MMGBSA kind of MMPBSA kind of calculations to have a crude estimate of the PCSK9 LDLR binding energy, and it shows, this distribution shows that depending on in which minimum that loop conformation is in, the protein ligand interaction or the PCSK9 LDLR interaction can widely vary. And minima 1 seems to have the least negative binding energy. So it clearly establishes that hypothesis that if you are closer to the more apo-like conformation of the loop, so these black one is more apo-like conformation. So if you are having a more apo-like conformation, that will have much weaker binding affinity with the ligand. So our goal would be to somehow stabilize the protein in this particular conformation. And we have some, and also it shows that each of these conformations have some specific hydrogen bonds, a set of hydrogen bonds. So this is just a proof of concept that we did some very rudimentary docking exercises just to see that whether we can actually stabilize this particular conformation. And with some molecules, we have been able to kind of stabilize this loop conformation, and it shows that in the presence of the ligand, presence of the inhibitor, indeed the binding affinity is much lower as compared to the normal protein without the inhibitor. Okay, so this is a proof of concept of our suggestion that we would like to kind of stabilize the apo-like conformations of the protein by locking that by using some inhibitors, so that we can lock those specific conformations of the protein, and this is our design strategy for allosteric inhibitors. Okay, so very quickly, I'd just like to emphasize at this point that it is not so simple. I'm going to now come to the difficulties that we encountered while trying to do more rigorous free energy calculations on these systems. As it turns out, that all these distinct conformations of the loops tend to be stabilized by very strong specific interactions, like a set of salt bridges or set of hydrogen bonds. So essentially, for example, as you can see here, that there are certain pairs of polar contacts and salt bridges. Some of them are present in the apo form and some of them are present in the bound form. So essentially, in order to describe this conformational landscape of the loop, one would need to invoke the contact, in some sense, the contact map. So a possible CV to describe the conformational landscape of this protein could be a vector of all these possible contacts. So this is something we are trying to work on now, that whether we can build a Markov state model by using either enhanced sampling data, like the Jagannath and others have been presenting. So I think that that the field to take, because simple, as I'm going to show you very soon, that simple CVs like RMSD and other has lots of limitations in characterizing this conformational landscape. So I'll just summarize the work at this point, that the several distinct loop conformations are stabilized by specific salt bridges and polar contacts, as I'm showing on the right-hand side. And this rewiring of this interaction network leads to this long-range communication. So starting from the binding site to these loops, there are certain important salt bridges that rearrange and that propagates this energetic perturbation. But the complete description of this conformational space would require a multi-dimensional CV. The simple RMSD is not really good enough, and I'll just take a few minutes to summarize that. So just to put this into context, that although we might think that these loops and the disordered regions of the proteins are not interesting, but as it turns out that these loops and linkers can play a very important role in the conformational dynamics and allostery, and they are really not just merely flexible. So one might think of them as, structureless, but that is deceptive, but they can be actually stabilized by a very specific set of interactions, and they can interchange. So essentially, they control the function of the protein by interchanging through these very specific conformations, which are stabilized by the specific set of interactions. Okay, so just the take-home message is this structureless and disordered loop regions may be potential targets for allosteric drugs, and the search for cryptic sites in the apo form is more probably crucial rather than in the hollow form. And the stabilizing these apo-specific conformations, which are less stable than the corresponding hollow conformation, will lead to this allosteric inhibition. So that's our summary. So Tarak, how much time I have left?
I think that's 1 + 4, 5.
Okay, so I'll just summarize the next parts in 2 minutes.
Yeah.
So I just wanted to, so our result and ideas are over. Now I just want for this community, I thought that I should share some of our doubts and difficulties that we faced during doing this free energy calculations, and hopefully I'll get some suggestions and insights from you. So essentially, the first problem that I would like to highlight, that the CV that we have used to construct the free energy surface, which is this RMSD, has a severe problem. But before doing that, let me just highlight a few problems associated with these distance-based CVs. So even with this simple toy model, let's say we have this simple bistable potential model, and if you run a simple Monte Carlo simulation, you are able to reproduce this simple symmetric bistable potential, which has equal stability. But instead of using this x coordinate, now let's say I use a different CV, which is a distance coordinate from a particular point. Let's say this -1. And so if I use this distance as a CV from this point, from this -1, so my CV now becomes this mod of x + 1. And then if you use that as a CV, what you see that the symmetry of the problem breaks down. So even in the free energy surface, it seems that the minima near this around x - 1 seems to be a bit overstabilized. because of the degeneracy associated with this distance around this point, because both this arm and this arm will have same distance from this point. And that this problem, this asymmetry is now being induced by this inherent entropy or degeneracy of the CV. And that becomes even more problematic when you have a many-dimensional system. So let's say now you have a kind of a 2D potential with this equal minima, and let's say now our CV becomes this distance from one of the minima. So technically all of them should be equally stable. That's what happens from a simple Monte Carlo simulation. But now instead of that, if I take a distance as a CV, as it turns out, this RMSD equivalent CV, as it turns out, you will see that the symmetry of the problem is completely destroyed, and you get to see only 3 minima. One of them can be hidden depending on where it is. So this minima is, so these 2 minima have equal distance, and this minima might get hidden depending on the distance. And even worse, the reference structure does not belong to the minimum, right? So this is a strange problem with RMSD like CVs, that the reference structure, which should appear at the distance of 0, that has a artificial entropic cost. So it really does not belong to the minima. And the same thing we have been seeing in when we try to use metadynamics and other things with this. So at the high RMSD region of the free energy surface, even if 2 points on the free energy surface are equivalent, RMSD does not imply that they are same structure. So on the free energy surface, they can be drastically different. So there is a huge degeneracy at the large values of RMSD. And so essentially, these structures can have, even they may look very similar from these 2 trajectories, but they can have energy landscape in terms of the interactions. And all this minimum are separated by large barrier. So it's something like a glassy landscape, where you can think about that in some regions of RMSD, there are multiple deep minimums separated by large barriers. So these are the kind of problems that we need to circumvent to properly compute the free energy surface of these loop regions. So we even tried with coordination numbers, but that also has certain problems that even after, there is a large degeneracy at coordination number 0. It is easy to break the contacts, but it's very difficult to make the contacts because of the entropic bottlenecks. Okay, so I think I'll just summarize with these take-home messages that these distance-based CVs may introduce some spurious entropic contributions, and these entropic bottlenecks are challenging in many of these CVs, and so often the local reaction coordinates are much better than the global, and contact map can be a better, robust descriptor. And many times, if you use a total number of contacts or total number of hydrogen bonds, that may give misleading conclusion because of the non-native interactions. Many times the total does not change, but because of this interchange, there is a cancellation and the distribution may change. Okay, so again, just to summarize, the combination of multiple CVs may provide a better mechanistic or physical insights, because different CV has their own pros and cons. So one has to do it very judiciously depending on the system. And of course, there are many more ideas that have been discussed in this conference. So at this point, I just thank my group. So the allostery work, the PCSK9 work has been done by Dr. Ikshita Basu and Shronak and Krishnendu. And then the first KR2 rhodopsin work was done by Dr. Muntu Shatra, Aniruddha Konkona. And for funding, I thank Surface Cure and ACRP and ISIN Bose Center. Thank you for the attention, and I'll be happy to take questions. Thank you.
Okay, thank you, Sumanda, and it's always great to listen to your talk, and I'm sure everybody has enjoyed it. And thanks for the last piece of things that tells us something about the pitfalls of choosing the collective variables overall. In fact, this Wolfe-Quaff model, I don't know if you have seen this, where or even Alain Dijkgraaf tried the sci-fi case, walking along one CV. Does a disaster. So sometimes a lot of hidden degrees of freedom we miss. Yeah. So probably that discussion will have a lot of follow-up discussions later on in this meeting. So thank you for that. And let's quickly take a few questions from the chat box. And Jagannath, would you like to ask your question?
Yeah, I think, at the later part, I think Suman almost pointed it out. I just had this technical question is that in the PCSK9 part, when you try to use the cluster 1 RMSD to do the umbrella sampling, so how did you generate the initial configuration for each of the window? Are this from this unbiased simulation that you basically have for this disordered loop? or?
We have used steered molecular dynamics to generate the intermediate configuration, and then from there we threw the umbrella windows. But we had lots of difficulty even in steered molecular dynamics. And
correct, yeah.
I did not go into those details, but it's a very challenging system which will
right
most of the existing methods.
Right, especially because you are talking about the clusters, that particular clusters RMSD, which will be a dynamic cluster also. So, it will always fluctuate. So I think definitely the later prescription that you had, this contact map, and somehow reduce the dimensionality of that contact map might be a very good strategy, I guess.
Actually, I was very much impressed by this Navjit's talk, and we are going to use similar kind of ideas. So I think that MSM is the way to go to characterize this conformational landscape here.
Yeah, right. Okay, thank you. It was very, as usual, very clean talk actually.
Thank you.
Yeah, so Anmol has a quick question that was a loop that you're interested in homology model. I guess, yes?
So, the crystal structure had two structures, one in the apo and one in the bound form. Both of them were present. In the apo form, the loop structure was there, but in the bound form, it was missing. So we had to model it for the bound form, but as it turns out, the model structure had a widely different structure, but which also tends to be very stable. So one of them were modeled.
Yes. Okay, thanks. So Kriti has asked something about the water model. I don't think water model plays any role here on the loop, let's say stabilizing the open state of the conformation.
Well, yes, it's quite possible. We did not look into the solvation coordinate yet. So obviously, the stability difference will be, so the solvation will be different between the loop, these two loop conformations. So it's quite possible that it may play a role. Yes.
Okay. So, I mean, he was talking about, I guess, the water model, TIP3P and something like that.
Changing the model, we have used the standard CHAM 36 force field and TIP3P water model.
TIP3, yes. Yeah, that's true. And the next one by Nayana. So when the hydrophobic gate opens, I could see the water molecules are escaping. What about sodium ions? Does the conformational fluctuations of protein help in the release of sodium ions as well?
Yes, actually the formation. So when the channel opens, there is a formation of the water channel, and that formation of that water continuous channel, that is crucial for sodium ion translocating. If you have a dry channel, sodium ion cannot pass through. So first there is an opening up. So hydrophobic gate stops the water channel from forming. Once the hydrophobic gate opens up, there is a water kind of comes in, and then that facilitates the sodium ion passing through. Yeah.
Okay, so I can see one raised hand. Professor Tarabdar, Professor Samni Tarabdar has a question. Please go ahead, ma'am.
Hello, Shumon. Once again, a fantastic talk. I just wanted you to go back and explain the entropic trap once more, because that is where most of the students get a bit lost. So what did you mean by the entropic traps?
Right. So let's say in this energy, on this free energy landscape, I would like to go from this end to this end. But as I have pointed out, RMSD seems to have a huge degeneracy. So at this point, let's take this particular point from this RMSD-based free energy surface. Even if I take two structures from the same point, they have distinctly different conformation, and they are characterized by completely two different set of contacts or hydrogen bonded network. So there is you can imagine there is a orthogonal coordinate, which is very slow because it has to make and break a set of hydrogen bonded networks. So there is a large number of configurations accessible within this range of RMSD, particularly in the high value of the RMSD. So essentially, high value of RMSD has a huge degeneracy, and even in the orthogonal plane, since there are so many different structures separated by this distinct set of hydrogen bonds, there tends to be very much slow dynamics in the orthogonal direction. And in metadynamics, then the problem becomes, so in the sampling, that as you are going, let's say I'm starting with this apo-like form, and it goes into this high RMSD region and it gets stuck there. It can break the contacts, but it's very easy to break the contacts, but then it cannot find the entropic bottleneck to make the new contacts. So even in the coordination number-based CVs that we have found, that it's very easy to, from the large coordination number, it's very easy to go to zero. It can break the contacts very easily, but then again, to find the right contacts, it has to enter the entropic bottleneck, which it cannot find. So it's like going from a narrow region to a wider region is easier, but from a wider region to come to a narrow region, very similar to that binding using metadynamics. It's very difficult to make a ligand to bind a protein, but unbinding is much simpler. right?
Exactly.
Indeed.
Exactly.
You have to use the techniques like funnel metadynamics and so on by restricting your configurational space, but it's very difficult to implement such techniques in these kind of systems. So there are lots of challenges. Yeah.
Okay, thank you.
Okay, Professor Srikant Sastry has a question, and please go ahead, sir.
Yeah, I was keeping quiet. I thought I'll ask you in private. So now just what you replied to Shrabani, you could in principle use some kind of a phase space factor to account for this kind of degeneracy, but I didn't at all understand the 1D example you gave.
Right. So essentially, for example, in this, I guess you mean about...
yeah, why there would be an artifact in the 1D case.
So let's say in this case, I know that there are 4 states which are exactly symmetric.
Yeah, no, this I understand, but the 1D case.
Yeah, but when I project without knowing about the system, sometimes if I just project on some arbitrary CV, and one might conclude that let's say this state is more stable as compared to this state, and so on and so forth, it might lead to some. So you need to know what you are projecting on, and you should interpret accordingly. So you cannot just. It's very difficult to correlate this projected free energy surface to the actual stability of the system. So that's what I was just trying to point out. Yeah. That on the projected free energy surface, we cannot just blindly say that this state is more stable than the other and so on. And also there can be hidden states because of the degeneracy. So these are the few points that I wanted to highlight. That's it.
Thanks.
Yeah. Okay. So that's great. I have a couple of questions, but I think I'll write in the chat box. So thank you again for the wonderful talk. And let's move on to the next one. Our next speaker is very, very special to me. It's my pleasure to invite Professor Shravani Tarabdar from IIT Kharagpur, and whom I know from last 1 decade and wrote the first paper. So she'll be talking about nonlinear reaction coordinates in enzymatic catalysis. So over to you, ma'am.
Thank you so much. And I understand that by asking the question, I have already tested my microphone. So can you see my screen now?
Yes. The screen is fine and the audio is also fine.
Okay. So let me go to full screen. Okay.
Okay, perfect.
So first of all, thank you, organizers, especially Jagannath and Nishant, for asking me to give a talk here again, because I have been a part of this RARE family from the very beginning, and I have been talking about the same system from 2014 onwards. So that basically tells that, probably I hope that at the end of the 15 years that I'm working on this enzymatic catalysis and using one particular enzyme, I have something to say and share with the students who are starting in this field. So the title of my talk is a nonlinear reaction coordinate in enzyme catalysis. And before I go ahead, let me thank the people who have made this journey really amazing for the last 1.5 decades. We started working on this problem with Dr. Arijit Roy, and to Pushpita, Sanjeev, and Tanmoy, I will give you only the last bit of the story today, which Tanmoy did just before he left for his postdoc. And the flag is being carried on by Shrutajit and Divya right now. And in between, I had great help from Bharat and Abhruni. So, and once again, thank you, Tarak, for being there. And I hope in the next RARE meeting, I'll be chairing your session. Okay, so now what happens over here is, I'm talking about an enzyme catalyzed reaction. And as you will see that throughout this entire procedure, typical chemical reaction being studied using these rare event methods, they are relatively less. I mean, yesterday, Carmine gave a wonderful talk where she was using the metadynamics to study the mechanism of a given reaction. And we have also been studying this enzyme family, which is a carbonic anhydrase, human carbonic anhydrase, which is one of the most investigated system, and therefore the availability of experimental data made it easy for us to use it as a template when we started our rare event simulation program about 15 years back. And the other good thing about this system is that its catalytic turnover is in the microsecond inverse regime, which says that if I can have the enough statistically important data in the region of 1 microsecond, which by the way is not so rare these days, I can actually test out several of the ideas that are being floated for phenomena which are associated with much, much higher free energy barriers. Okay, but so let me get back to the exact problem that we face in studying enzyme catalyzed reaction. For example, for this enzyme, what I have is this is the actual chemical reaction, which is the target of this special function of this enzyme. It catalyzes the conversion of carbon dioxide to bicarbonate. But interestingly, this is not the rate determining step in this process. The rate determining step is the conversion of the catalytically inactive form of the enzyme back to its active form so that it can go on catalyzing this entire reaction in a cyclic process. So then our idea was, okay, let us use this catalytically inactive form, which has a very well characterized crystal structure. And let us take this catalytically active form, which also has a well characterized crystal structure down to the resolution of about 1 angstrom. And let us have a look at what makes it so special that this enzyme is one of the best enzymes available in the literature. So when we started looking at this a little more carefully, we understood that there is a intramolecular proton transfer reaction, which is constituting the heart of this rate determining step. So the basic idea then was, okay, so probably what we need to look at is how the catalytically inactive form gets transferred to its active form through this intramolecular proton transfer, which involves specific reorganization of the environment of the catalytic metal ion at the active site, reorganization of the hydrogen bonded water network at the active site, and eventually delivery of the excess proton at the edge of the active site, whereby one specific residue will shuttle it out of the active site. So there are several intermediate steps involved. And to tell you the truth, when we looked at the high resolution crystal structure, we could see the hydrogen bonded network. And from the kinetic data from a wide range of mutations, we knew that there is a set of amino acid residues surrounding the active site, which are extremely important for the kinetics of this entire process. And we could also understand what would be the entropic demand on the formation of these proton transfer pathways, either involving 2 water molecules or unbranched chain of 3 to 4 water molecules, and so on and so forth. But if I just look back into the domain knowledge and try to understand that if I have at least some 2 to 3 picoseconds of such well-formed hydrogen bonding, in that case, obviously, with the perfect orientation of 2 water molecules will require less than 15 femtosecond for the proton to zip from this water molecule and land up over here. And this would be a little more as I go for the increased length of the proton transfer chain. But there is no reason to expect that this process will take anything more than 50 femtosecond to transfer the proton through these about 10 angstrom distance from a zinc-bound water molecule at the active site to the edge of the active site. Then the question was, then obviously I need to understand the role of the protein matrix over here, including the mutated residues that we see, which affect the rate either in a positive way or a negative way, as well as the role of water molecules together to produce this this extremely efficient enzyme which works in the microsecond time scale. So that is where we started carrying out our very detailed modeling of the system. And we immediately understood that even if the biochemists would like to write this in a very simple way, in a schematic way like this, and we would be tempted to construct a reaction coordinate, which is just a single reaction coordinate that transfers the inactive form to an active form. This may not be so easy. And then it came to us the question, like the reaction coordinates involved here, do I need to use single or multiple reaction coordinates? And that was backed up by our study on multiple sets of transition path ensembles, which we generated for different variations of these catalytically inactive form into different other conformational parts. So what we had was volumes of data, but they were very closely related to specific processes, like what are the different channels which can modulate this catalytically inactive structure, and what are the different mechanistic channels through which these collection of different starting points can get converted to the catalytically active point, and if there are several other intermediate states involved. So to solve this apparently very simple problem, what we really needed was to go back to the experimental data, use the domain knowledge, and use the experimental data very carefully to set up a microkinetic scheme, which gave me all the alternatives accessible to study the conversion of this starting state to the ending state. So I'm not going to go into how we came up with the most probable microkinetic scheme for the transformation, but I will just highlight that our basis of studying this was different ensembles of transition paths, which we developed for different mechanisms. And from there, we developed the most probable mechanism. Now, when you have a microkinetic scheme for the most probable mechanism, then our basic idea was, okay, for each of these steps, let me get the reaction coordinate. And once I get the reaction coordinate, then I can basically go ahead, calculate the free energy and kinetics along the one dimension. Then I can assess the mechanism of catalysis and go back and forth. So these are the two steps that we iteratively improved on to get the most probable mechanism. And then try and see if we can eventually reach the dream goal of using our results to facilitate the design problems, because the template enzyme that we are looking at is already a big target in pharmaceutical research. Many of its inhibitors are actively used as drugs, and still one doesn't know the isozyme specificity of these drugs, and leading to several side effects. And more specifically, there are certain isozymes of this enzyme which are extremely important in cancer research these days. So that is our ultimate goal. But for today's talk, I think I will be addressing mostly the practitioners and highlight some of the little hitches that Shumon very nicely summarized in the last part of his talk, and share some of our learning experience with that. Okay, so what we start over here is by looking at all these, some kind of a most probable kinetic scheme when I go from the catalytically inactive state to the catalytically active state. And our basic idea is for each of these steps, I will obtain the reaction coordinate, and project the free energy along that reaction coordinate, get the kinetics, compare the overall kinetic scheme, and identify the most probable mechanism by analyzing the individual rate constant. So the classic textbook physical chemistry exercise that you can talk about, but our challenge was to get the individual rate constants. And obviously, in order to have a realistic representation of the mechanism, I needed to have the reduced dynamics along each step consistent with the full phase space dynamics along the given reaction path. And therefore, when we started with, there were quite a few questions that we faced. So how do we obtain unbiased reactive trajectories? Then obviously, how do I choose the collective variables for my chosen step? And how do we combine these CVs to formulate the effective reaction coordinate for my system? So as this has been elaborated upon extensively in this conference, I do not need to go into the details of what a commuter is, but for us, commuter is the ideal reaction coordinate for each of the small microkinetic steps, because it preserves the reaction rate from the multidimensional free energy space underlying my problem. And I aim at using really long classical MD simulations or QMMM MD simulations. And if the barriers are high between the intervening states, I can also use the transition path sampling to construct an ensemble of trajectories which connect my starting state and my ending state in each of these small microkinetic steps in my overall transformation. So, and that I'm going to use to estimate the commuter. Now, as you understand that even the definition of rare has changed when we started working on it in way back in 2009. So at that time, what we did was we just started by following a single order parameter, and we were looking at a local conformational fluctuation like this. And it was a big deal for us to simulate even up to 5 nanoseconds of molecular dynamics simulation, all atom molecular dynamics simulation, to observe a rotation like this. But what we could do is we could use an umbrella sampling and find out that, yes, we indeed have somehow high barrier separating the two conformation states. So we decided to shoot transition paths sitting on the top of the barrier and try to look at if the single order parameter can serve as a good reaction coordinate. Now, let me clarify at this stage that when I talk about an order parameter, this is that special CV that can unambiguously distinguish between the initial state and the final state for any given transformation. And a reaction coordinate for us is one that will give me a distribution peaked at 0.5 if I look at generated distribution sitting at the barrier top. So this is the what is the so-called commuter distribution for the single order parameter analysis. And we find that even if the our simulations, which are, I think I should be really embarrassed to put these numbers up these days. But as you see, even with these very rudimentary calculations, I do find that the distribution is not too bad. And this is exactly the collective variable that you would use this is a side chain dihedral angle. And this is one of those important collective variables that you use to mimic the transition or follow the transition from one initial state to the final state. But at this stage, we did not have any real way of checking how good my commuter is as a reaction coordinate, because well, there was no direct way of comparing it to experimental data other than looking at this distribution. So what we do is then we said, okay, let us take the this entire calculation forward, but we obviously need an alternative approach, because the National Supercomputing Facility came to us only about 2 years back. And for 1 microsecond sampling of each of the small microkinetic steps parallelly. It took 2 graduate students 5 + 5 years in parallel. So we obviously had to devise some alternative approaches to estimate the commuter. We said, okay, we will still work with our transition path ensembles, but we will look for a special coordinate, which we'll call the reaction coordinate, which we will use as a combination of order parameters. And once I optimize this order parameter, then I'm going to construct the commuter from it by either as a tan hyperbolic function or as a sigmoid function. So that gave us the poor man's or poor woman's option for a one-pot method based on transition path sampling simulation. So what we did was, we certainly had this kind of what we love to call as a primary order parameter. This is one CV that I must have to start with, which can unambiguously distinguish between the initial state and the final state for any of the microkinetic step in my conversion. And then we sit in the intervening region and keep on shooting trajectories. And we have a total, say, NSP number of shooting points. And some of them land in the initial state, some of them land in the final state. And without incurring any additional computational cost, we select only those order parameters which have such distinguishable distribution at the terminal states. So within the framework of transition path sampling, we not only had a good handle of looking at the mechanism, but also a good way to distinguish, to pick up, cherry pick these order parameters, which are giving me these kind of distinguishable distributions at the endpoints. Okay. So now let's say that I have these order parameters, a set of order parameters, which I process through renormalization. I compute the covariance matrix, and then there are many things that I can do. And so what we do is, we actually carry out a principal component analysis, which obviously is a linear combination, gives me the reaction coordinate, that special coordinate R as a linear combination of the order parameters that I have chosen over here, in such a way that I maximize the variance with respect to the shooting points that I have used. I could also have computed the takes, and as I will show you later on, this is what we have started using once we could go for typically a microsecond of long simulation, as soon as the supercomputing facilities have become useful to us. But going back, when you have a very high barrier and you do not have sufficient data to tell you what the obvious CVs are, so what we do is we still use the transition path sampling and then express my reaction coordinate R as a combination of these sum of all or some of these order parameters that I've chosen, and I maximize the likelihood of such model by combining them. Now, this is the classic original version of the process, which was given by Peters and Trout way back in 2006. And they also give us the flexibility of using a Bayesian information criterion to decide on how many order parameters I should use to construct my reaction coordinate. So my reaction coordinate is that single special coordinate, which I am trying to construct out of my at least 1 or 2 or 3 or 4 order parameters, depending on the set that I have chosen. And once again, as you see, that the best model depends on the number of shooting points or the number of realizations that I have over here. And obviously, once you have the reaction coordinate, you know its dynamics, you can construct a transition matrix and use the latest methods. For example, the entire setup of Markov state model is available to you. And you can use different variants to get the dynamic histogram analysis method or the mean first passage time to get the rate constant. So now, once again, let me go back to the use of my transition path ensemble to identify some of the major mechanistically important channels that I have over here. And what I would like to mention here is the importance of identification of these mechanisms, because as I see that I was interested in how this state goes into this state. And now I find that these two states are modified. The transition are dominantly modified by not only conformational transitions, but processes like the coordination environment of the metal ion changing because of coupled motion of water molecules with active site amino acid residues. And then you have some intramolecular and intermolecular proton transfer reaction. And therefore, we concluded that having a single reaction coordinate will give me, obviously, a rather low resolution representation of the entire thing. But I will lose a lot of important information if I overlook the different mechanistically important procedures. So let me have a quick look at the results from the linear models of the reaction coordinate. So actually what started out 15 years back as an infrequent conformational transition, these days with the availability of supercomputing facilities, we can just have these 1 microsecond long trajectories. And we actually can see that there may be more than one collective variables which have quite distinguishable distributions at the end states, and we can construct the free energy surfaces. And when we try to look at the mechanistically important minima and identify the kinetically accessible regions, we do find that these conformational contributions that I see over here, they are having rates in the range of 10 to the power of 6 to 10 to the power of 8. And on the whole, although there are some contributions which are even as slow as the overall kinetic scheme, there are contributions which are much, much faster. Okay, and not all these conformational states are relevant to the actual structures which will undergo the next stage of chemical reaction. Actually, what we find is a mixture of the states from which these conversions occur. They give you 10 to the power of 7 second inverse as the effective rate for the use of the chemical reaction that follows. Now, if I put in the rate constants for each of these individual steps, I find that this is the step that gives me the slowest rate, and this would dominate the entire proceeding. Now, obviously, we then got the question from all the reviewers that what if your whatever you are using here is a linear combination? Good, but what if you used a nonlinear reaction coordinate? So we decided to focus on the slowest step, which is the chemical step of intramolecular proton transfer. And what we have here is we decided to go and look back at our transition path ensemble. So let me give you a little bit more detail of what I have here. So what I have here is my protein in water, and the QM layer, we are carrying out QMMMD because obviously we are doing here an intramolecular proton transfer reaction. We extensively benchmark the system against by having some DFT based characterization of the QM region. But eventually, since I'm interested in looking at a rather big ensemble of transition paths, we had to settle with semi-empirical methods. And the MM layer, we use this AMBER FF99 SB force field. And with that, I have some 1242 instances of transition paths, and which are 1 picosecond each. So basically what I have here is that I sit on the top of the barrier region for this chemical reaction, and I shoot transition paths. And so I have more than 1 nanosecond of QMMMD snippets of the reactive event. Now, before I do anything with this, So I need to understand what my primary collective variable is going to be. And so Tanmay came up with this very interesting idea of having a mean path, because unlike Carmen, where she had two specific bonds and one angle in describing her reaction, here we had many things going on, and we needed to have a rather coarse-grained description of the extent to which the reaction has proceeded at a given stage. So we use this mean path, which is basically telling us about the fraction to which the entire path between its starting point to the end point has been crossed. And it gives me very nice separation of the reactant state, product state, and the intermediate region. And it also tells me that if I look at the terminal states, distribution of this mean path from the terminal states, it gives me a clear-cut distinction of values, making it a candidate for my primary collective variable. And we then decided, okay, for this transition path ensemble, let us look for other collective variables which have distinguishable, within quotes, distinguishable distributions at the two states. And unfortunately, we find none. So, but since we are trying to test the effect of these collective variables over here, what we have decided is, okay, let us fix some of the adjustable parameters that we have here. So I will fix my analysis to 6 collective variables, only one of which from my transition path ensemble gives me a clear-cut distribution at the endpoints, but the others will have distinguishable peak positions in their values at the endpoints, but they will have overlaps in their distribution of values on the whole. And now I'm going to use the neural network as the means of generating a nonlinear, both linear and nonlinear reaction coordinate starting from these 6 input CVs. And what I will test at the end of it is the PB of the system. Now, obviously, to train my neural network, I then require to go for an explicit calculation of the commuter. So in order to do that, so what we do is we start from nearly 80,000 shooting points. And then from each point, we have 100 additional shooting of QMMM trajectories. And then we calculate the commuter and we bean it as a function of our primary collective variable. And we see that this is my training set for the neural network. And then we go ahead and have 4 different models for my reaction coordinate, okay, where I have started from 6 CVs. I have combined the CVs either in a linear fashion and used either my likelihood maximization method or a minimization of the mean square error within the neural network, or I have tried out some specific forms of the nonlinear model, either through a manual choice or through the artificial neural network, and went ahead and calculated the reaction coordinate using the transition path ensemble to it. So right now you need to understand that I have one single step and I have 6 collective variables, which I have already shown to you. And I am using 4 different methods to calculate the reaction coordinate. So these are the reaction coordinates, how the reaction coordinates vary. So if I just pick up this, the final one, the one that I have got from the artificial neural network, I start from this barrier region. And then my R for some of the trajectories, they monotonically continue to the reactant region, or they monotonically continue to the barrier region. So basically, if I follow the reaction coordinate, it has this dynamically also, its evolution distinguishes between the 2 states that I am talking about. And then we also look at the difference that, so if from here, I do not see much of difference between the dynamical aspects of the individual reaction coordinates. But if I look at their individual relaxations, so this is the autocorrelation function, normalized autocorrelation function that we form, we find that the artificial neural network has actually picked up the fastest of the combinations, fastest decrease of the combination among all the 4 models. And if I look at how well my computed reaction coordinates samples my test set, I find that obviously the artificial neural network has been trained to capture the wide range of, yes, Tarak, I understand that I am running out of time. I will try to summarize as quick as possible.
Okay, thanks.
But the linear models, they are unable to reproduce the width of my barrier region as far as this two-dimensional map is concerned. Then the question is, whenever I'm doing this kind of reaction coordinate model, am I picking the right kind of direction in going from my one free energy minimum to the other free energy minimum? So we actually went back and did this calculation where we could compare in the 6-dimensional space the direction of transition. And here we have compared it to the direction of the second tick as I go from this minimum to that minimum and represented it in the Q1, Q2 subspace. And we find that we are actually doing pretty well, even if we use the linear or the non-linear, linear combinations, either within the neural network or the likelihood maximization process. The free energy profiles are very similar, but not really. But the most important thing that we come back over here is whether these models are capable of reproducing the quantities which are important for the final model building or the comparison with the experiments. And we find that the experimental value of the free energy activation barrier is most faithfully reproduced by the artificial neural network reaction coordinate. And it also is capable of reproducing the rate constant. But we also notice that the rate constants, as you see, that they are not so sensitive towards the choice of the method by which I model the reaction coordinate. So we have heard from Professor Bagchi earlier in this particular edition of RARE that the computed rates would very much depend on the number of order parameters that you're choosing. So we decided to have another set of extensive tests where we take our 6 CVs and put them through the extended auto encoder method and ask them to stand the test of this extended auto encoder method by asking it to go through the encoding, decoding process and see if any of them satisfy the condition of being reproducing the PB value that we have here. And what we find are our original primary collective variable mean path is the only one which sort of stands the test. So this is the most important collective variable in our analysis, and the rest of it, they are not suitable. So obviously at this stage, we are a little confused, and we went back. We repeated our calculations by having only the mean path as a reaction coordinate. And then we find that if the best reaction coordinate that I had was a linear likelihood model and the ANN models, all of them are overestimating not only the free energy of activation, but also it is grossly overestimating the rate constant. So we obviously had to revisit the collective variables that we fixed at the beginning of our story. And so what we have here is just by using the framework of transition path sampling, we actually found that having this distinguishable distribution at the 2 endpoints is a good enough criterion, which also stands the test of an extended autoencoder model. And the rest of it that we find, they have been rejected if they have an overlapping distribution at the terminal states. Now, so what we did was we once again looked back, and the linear model does fine. We really need not have gone into the nonlinear model in this situation. They were doing fine. So what we did was we looked into the form of the linear model. So this is the contribution coming from the most important collective variable, and this is the contribution coming from the other collective variables that we see. That's very difficult to interpret anything from their individual relaxations. But if I look at the way this mean path, the contribution to the mean path comes into my overall dynamics, I find that this is the only one which dynamically reproduces the distinguishable path distribution in the two states, while the rest of the variables, they provide just some noise. And this is the perfect Gaussian white noise that is being provided to the slow mean path variable. So what is the take-home message from here? You can very well argue that the individuals collective variables that I see here, they are not always very slow or very fast compared to the major collective variable that I have picked up over here. But as you see, that a particular combination, my reaction coordinate, is giving me a particular combination where their dynamics cancel out each other, forming a uniform noise background to the actual reactive reaction coordinate, which gives me the insensitivity of the reaction coordinate towards the rate calculation. And as expected, this is not so as far as the free energy calculations are concerned. So where have we reached so far? So at the end of 15 years, I can say that starting from a picture which a biochemist would love, to explaining what exactly is the source of the free energy barrier over here. It is a transformation between the eigenlike to the Zundel-like nature of the excess proton that is being transferred to an artificial neural network. What we have learned is reduction of dimensionality is absolutely necessary, but let us do so by involving mechanistically important CVs. And I must emphasize over here that while constructing the most probable kinetic scheme, we had to investigate for very unusual molecular mechanisms like the coordination dynamics around the catalytic ion, which actually helped us in retrieving the correct kinetics. And obviously, at the end of the day, the scientists prevail over big data analysts, and therefore we are still relevant even if we are working on the same problem for 15 years. I must thank my institute for providing me with the computational facilities, and none of these work would have been possible unless and until we had this national supercomputing mission facility established at my institution. And finally, thank you for listening to me.
Thank you, Professor Tarak, for a wonderful talk. And I'm sure this kinetics and rate constant will be looking forward to these things more in the future, and they're very tricky to handle. Anyway, so let's have a quick question session. I think one question from Pallav. Can you please elaborate a bit how Bayesian information criterion is used to choose among CVs?
Okay. Actually, I'm sorry, I did not try to explain it too much. So if I go back to my slide over here, as you see that I have a total of, say, some kind of n order parameters, okay? And I'm combining, I'm now choosing some other number of order parameters out of my total set, okay? So as you see, if I have, say, I have identified 4 order parameters, I can now build the models for R with 1 order parameter, 2 order parameters, 3 order parameters, and up to 4 order parameters. There will be only 1 4 order parameter model. There will be 4 1 order parameter models. Then we started asking the question, what is the best 1 order parameter model? I'm sorry, I had this slide, I deleted it. So we ask for what is the best 1 order parameter model. So let's say that Q1 gives you the best 1 order parameter model. The combination of Q2 and Q3 gives you the best 2 order parameter model. Then it's something like that. Then my question is, should I use the R, which is a function of Q1, that is my 1 order parameter model of R, or the R that I have got from the 2 order parameters as a combination of Q2 and Q3. So if that happens, then that is where we use the Bayesian information criterion following Peters and Trout, it says that, well, how many realizations of the commuter do you have? So if you have NSP number of realizations, then what you have done is you have built your commuter or your special reaction coordinate with two models. One is with n+1 order parameters, another one is with n order parameters. What is the likelihood of each of these models? So you pick the likelihood of each of these two models and take a difference in the logarithm of them. So basically then you can, I'm not a practitioner of information theory, but it can be shown that the information content of the n+1 order parameter model is more if over the n order parameter model, if this criterion is satisfied. Okay, so you have to have the standard background set of realization of the commuter and the number of order parameters that you are using to model the commuters at individual level. Did I answer your question?
I hope so. I think, yeah. So let's thank Professor Tarak again for the fantastic talk. And I'd like to thank all the speakers of this morning session for their wonderful talks. And I'm sure all participants, they've learned something new, something exciting. And now I'll hand it over to the organizers if they have any announcement. So Nishan, please.
Yeah, thank you, Jagannath. Sorry, thank you, Tarak. I will ask Jagannath to add something.
Yeah, I think I actually would like to first thank Tarak to help us out here with the chairing these sessions and basically intriguing questions that he has basically brought out throughout the symposium. And what I really would like to request that many of the seminars that we actually had, most of them are going to be recorded. All of them are being recorded. So as we see that because of the time zone issue, many of the participants could not attend it. But I am just expecting that maybe in the brainstorming session, everyone will at least participate and try to complete it. So today we have seminar started again in 7:25 p.m. correct? IST. Yesterday we had 8, but today we'll have 7:35. So basically, I hope that all of you will basically join us. And basically, thank you very much. We'll just close it here then.
Thank you. Bye.
Bye.